Hello. Hello, good morning everyone. Good to see you again and welcome to the day 2 of the Gian program. So, next generation sustainable alternative proteins for food, fundamentals and technological innovations. And unfortunately, we could not cover the lecture 2 and tutorial yesterday. So, but we are going to cover that today. So, today we are going to have 3 lectures. The first one is global trends and market opportunities in alternative proteins. And the lecture 3 is about how we can extract proteins from different biomasses, what are the conventional methods we have, and lecture 3 about some of the new or innovative or emerging methods to extract proteins from different biomasses. I'll try to give some examples and some success stories. And then at the end of the day, we're going to have a small tutorial where we're going to discuss about the market opportunities or different sources of plant-based or alternative proteins. Does that make sense? Good. And did you enjoy my lecture yesterday? Okay, then it comes my very first question for you. What is the most important thing that you learned yesterday? Just raise your hand and just mention, yeah? Maybe you need a mic, yeah. So, your name please again? Akib. Akib has a point, yes?
So, insect proteins could be really one of the best alternatives for the animal proteins.
Super. So, he thinks that there is a future for insects and insect proteins.
Yeah, because
That's
of
good.
their composition and all other functional properties.
Exactly. It has a very good protein functional properties and protein quality in general, good amount of essential amino acids, and digestibility is also apparently good. But I did not cover, for example, allergenicity aspect, other thing. There are some limitations as well. We will take it in some other lecture.
Okay,
Good.
sir.
Yeah. Any other important thing you learned among the audience? Yes, there is a, yeah.
Good morning, sir.
Morning. Yeah.
There is a high need for changing the protein sources. We are conventionally following some sources which causes environmental impacts. Whereas in current situation, we are about to think in an alternative perspective, considering the global sustainability and environmental impact.
Absolutely. That is a very important remark she made. Your name please again?
Niveta, sir.
Nivedita. So, that's the whole point of my lecture, I would say. So, I really wanted to showcase you that the current sources what we have been using for proteins, perhaps it's not very sustainable. Considering the environment for the future, we need to start looking for alternative food sources, in particular alternative protein sources, because protein is an important part of our diet. Very good point, appreciate that. Any other comment? Any other point you learned? The last one. Anything? That's all right. So, I think we covered 2 most important things, but of course, there is also another important point we learned is that we can also go for some of the aquatic sources to get proteins. For example, microalgae, because they often consume less space, less water, and still produces high amount of high quality proteins. So, there is also future for microalgae and microalgae based proteins. Okay, now I'm going to talk a little bit about the global trends and market opportunities in alternative proteins. I must mention that this is not one of my favorite topics to teach because I'm a scientist, I like teaching science, but it's very important topic because without market, in most cases, as a food scientist, for us it's very difficult to do research and development. Do you agree? Food science is often considered as an applied discipline in science. Why? Because we talk about manufacturing of food, we talk about modification of food, we talk about creating of new food and so on. Why are we doing this one? For the benefit of society, right? Somebody has to eat the food we have created. Somebody has to eat the taste we have improved in particular food, for example, right? There should be some consumer who should wish to have the protein or any other food matrices we have created. There should be a market for that. So, without market, I am always saying that maybe our discipline it will be very challenging situation for us, though we do some fundamental research in food science and technology. All right, now I'm going to talk a little bit about what are the global market trend and where are we today with respect to alternative proteins. And this is one of the nice figure, I got it from a review article from Annual Reviews in Food Science and Technology, which clearly nicely illustrates where are we at the moment and where we are going to be in the future when it comes to alternative proteins. Now we can see that we are actually somewhere in this particular region according to me and the current place, starting from let's say 1980s to let's say this is 2020 ish 2025 now. So we are in this particular region at the moment. As I mentioned, soy is one of the most well established so-called I don't call it as an alternative proteins, but it's one of the most established alternative plant-based proteins. The structure is well known, the functionality is well known, and it has been used in numerous products, and that is currently available in the market. Soy protein isolates, for example, soy protein concentrate, for example, have been used in numerous products. I'll give some examples later in some of my slides. And something also being done with pea, and I mentioned that considering the sustainability issues with soy and soy production and soy processing and problem with the traceability of soy based products, now people are more leaning towards pea as an alternative plant based proteins. And it's also important that to mention that soy and pea cannot be grown everywhere in the world. There are some regions they can grow soy, there are some regions they can grow pea, and depending on the local cultivation tendencies and the things will change. For example, in Europe, for example, let's say you can grow more rapeseed, that means they try to valorize how we can use rapeseed proteins. If you come to Americas, they grow a lot of soy, and then they think about how I can use soy and soy based proteins in their products. That varies from region to region, just to let you know, it's not very universal. In India, if you say that, okay, we produce a lot of millets, we produce a lot of moong, probably we need to start using moong based proteins or millet based proteins, so it varies. It's very important to mention that when it comes to market, we produce something, we consume in the local region, and there is also an opportunity for transporting into some other part of the world. And then sometimes it's easy and sometimes it is challenging, because transportation always brings another environmental footprint, because it has to go through the flight, it has to go through the ships. Again, there is an environmental footprint. So we always have to think in sustainability point of view, grow locally and use locally, probably that is more environmental friendly, and that's one of the approaches within the sustainable developmental goals. So we need to think about local sources and local utilization of food and food ingredients. Does that make sense? So in the future, so we are going in this direction. So I could not cover the fungal sources, but I had some slides, but we had some time constraint, but I'll cover about fungal sources of proteins in one of my future lectures. So in the future, we are also going for fungal, but I don't say that we are not using fungal today. We are using, for example, there is called corn product, Fusarium species that produces a lot of single cell proteins, extremely good in the essential amino acid composition, low amount of mycotoxin. So it's already in the market, especially in UK, and there are 10 different countries apparently selling fungal based products as a meat alternative. So it's already in the market, but there is more opportunities using different kind of fungal sources to produce single cell proteins, and this is where we are heading in the future. And in next let's say 5 to 10 years, I'm not very sure, this is a number game, it's very difficult to say when we are going to eat algae completely, but it might be 5 to 10 years or 10 to 15 years. So we going to use mostly algal based or insect based or other kind of proteins in the future. I don't say that algal proteins are not available, it's available. For example, spirulina is commercially sold in many parts of the world. Algal ingredients are also available, but the biggest challenge is that it's not universally available. Why? Because every country has their own regulations. So we can't sell every product in every countries. Every countries will have their own food regulation bodies, and they have a strict rule on, okay, are you able to market this particular product to my people? They say, no, it's not possible because our laws are not accepting these kind of proteins. And there is a glitch, there is a market problem here. So things are not universal yet, it is actually varies from local government to local government. Just to say an example, European Union has their own regulations. There is EFSA, European Food Safety Authority, and they have their own regulations, and basically you can't sell every product in Europe, for example. They have these novel food categories. They say that, okay, if this protein comes from this particular species, no, you can't sell it. Only this protein coming from this particular species can be sold in European market, and with the label called novel foods or novel protein, something like that. So it varies from country to country. Does that make sense? So it's not a universal truth that the protein can be sold everywhere. It changes. All right, so now I'll talk a little bit about some number games. So I'm not very 100% sure that these numbers are 100% correct, because I'm not a market specialist. I have taken it from the internet, from the reputed sources, for example, but I still believe it's a good number, at least for the approximation. So the market value today for the alternative proteins around 90 billion US dollar. That's a big number, but it's not an extremely big number. Why? Because if you take a, let's say, meat market in general, even today the meat market is around 1,000 to 1,500 billion dollar. It's around 10 to 15 fold higher than the alternative protein market. So we are going in this direction, but we haven't matched with the meat or dairy. Dairy is, I think, around 1,000 billion dollar, something like that. So we are about 10-fold lower when it comes to alternative proteins, but still it's a big number according to me. 10 is not a small number to say, right? The US is one of the largest producers and consumers of alternative proteins. It's around 12 billion US dollars, and the European Union has a lot of different countries like Denmark, France, Germany, Italy, and so on. They're all together constitute around 6 to 7 billion dollars. They are the second most consumers or producers of alternative proteins, just to let you know. India is not yet in the top positions, but we are also going in this direction. There is some increased, apparently there was some research laboratory they're working on, for example, cellular agriculture, what we call that. You can cultivate meat in the petri dish. If you have studied biotechnology, animal biotechnology, animal cell culture you have studied perhaps, and you can actually cultivate meat on a petri dish, and that can be eaten. Singapore has sold their first cellular agriculture product in a burger or something like that. So India is also going in that direction, but I don't have a specific number. Where are we at the moment in terms of alternative proteins? Okay. And when it comes to the market share, it's basically the plant-based is the majority one, and then food, and then the rest is, for example, the insect, microalgae, and other things are covering about 20-25%. So plant-based is still 75%. Its majority is plant-based. Okay, and when it comes to the market, food and beverage is highest one, and the small portion is going for the animal feed. It's basically we are using alternative proteins for the food purpose, not for the feed purpose. I hope you're sure to know what is different between food and feed, right? Feed is basically for animals, and food is for, we are also animals, but we are human, clever animals. So food is for us. So it's not redirected to feed. I have to mention this point very clearly, because if you redirect alternative proteins for feed purposes, then we again question the sustainability issue, because then we need to consume animals again for the same proteins, right? And then again we come back to the same loop. But in some cases it's also used for the feed purpose. Let's say for insects and something, maybe you have to convert some bad protein into good protein. Bad protein in the sense the protein is, let's say it's not digestible, probably you can convert it into more digestible proteins by giving it to certain animals, because they can biosynthesize high quality proteins. So we can again make them as a high quality proteins. Does that make sense? And this is an important point I want to mention, that why the today's consumers are looking for alternative protein sources. What is the driving force in them? The first one is that the health consciousness. How many of you think alternative or plant-based foods or plant-based proteins are healthier? Raise your hand. How many of you think that? There's 1 person, 2, 3, 4, 5, 6. There's a lot, right? Almost like 60-70% of the classroom thinks plant-based proteins or plant-based foods in general are healthier. Maybe someone could elaborate. Why do you think so? Is it just a gut feeling, or is it just a trend? Now our director was telling Generation Z or something like that. Is it something that feeling? Yeah, there is somebody want to answer something. Yeah, yeah.
Sir, it produces very less carbon footprint when
Yeah.
compared to meat.
Yeah.
That is the main thing. And obviously, it is cheaper than meat based.
So what he is thinking that coming back to our yesterday's lecture, I gave like 3 hours lecture saying that animal and animal husbandry is related to greenhouse gas emission, a lot of carbon footprint, environmental footprint here. So to avoid that, I want to eat more plant-based or more alternative sources. That's his feeling. I want to save the Mother Earth. That's super good. And he also mentioned that cost. So the second point, he thinks that the vegetables are less pricier compared to meat, at least in Indian context. I fully agree that. But if you come to Denmark, I'm always scared because usually their chicken was much cheaper than the Indian grown vegetables. I can tell you that I could get 1.3 kilograms of chicken for, let's say, 40 to 45 Danish krona, and 1 kilogram of let's say Indian vegetable, let's say Karela, right? It was 75 Danish krona. Of course, it comes from India. Sometimes the price parity is different depending on from which country it originates and where it is being sold. In India, I know that the vegetables and fruits may be expensive. Vegetables are much cheaper than the animals, right? Probably I don't know about the ingredient market. That's another story. That's another group, because the whey proteins, I don't know whether it's equally priced as soy proteins, but soy proteins are much cheaper if I'm not wrong compared to milk-based proteins. So it varies. Good point. Yeah. Any other reason why do you want to go for plant-based stuff? Yes, she has a point. Yeah.
So, as per the human consciousness, I feel that they are having the meat-based proteins. They are having negative emotional
Yes.
feelings.
Yes.
Because animals are crying and we are slaughtering them.
Yes.
Right. So, to have a positive, in fact, feeling of a food.
Yeah.
That matters a lot.
Yeah.
For the Hindus people, I feel.
Yeah. Yeah.
Okay.
Yeah.
Right.
Yeah.
First thing is this, and second thing, it not only gives you the protein, it also provides you the active components or the other phytonutrients, which are essential for the human body. Like it can be micro minerals also, it can be microvitamins also. So that means not only we are getting protein, but we are getting the protective nutrients as well.
Absolutely. That is a very important point she has raised. Thank you for that. What she thinks is that there is an emotion among ourselves. Okay, we need to save our animals. Animals in some regions, in some cultures, it's our sacred things. We don't want to slaughter them. We don't want to kill them, right? So there's a feeling. And you know that there's a huge global trend towards going towards vegetarianism and veganism and something like that. It's a huge trend. The young generation would like to completely change their dietary habits. Maybe they were born as a mixitarian or flexitarian or something like that, and now they want to become vegans because they have this ideology saying that, okay, we don't want to harm the animals. Animals are not for the benefits of human beings. They have their own life, they have their own families. We don't want to disturb them, and the vegans don't want to drink even milk and milk-based products, right? That's another reason why there is a global trend towards plant-based and alternative proteins. And the second thing she mentioned that especially plants, microalgae, and also insects, they're not just protein sources. Sometimes they can also give bioactive compounds, especially plants produces secondary metabolites, let's say phenolic compounds and let's say some kind of other metabolites, and they have an added advantages. You have to eat more fruits, not for necessarily the proteins, because the protein content in fruits may be 2, 3, 4%. However, it contains some other components, anthocyanins, that's good for your body, right? vegetables is not just for proteins, it contains other vitamins and trace minerals and so on. It's actually a complete food that we want to eat, and that's the reason why people have a tendency to go towards plant-based foods. Any other reason? The last one would somebody wants to mention? Yeah, there we have one more person.
Good morning, sir.
Morning. Yeah.
Meat-based proteins have more fat content than the plant-based proteins.
Yes.
Means they rise the cholesterol level, which is not good for the body, and that can lead to many diseases. Also, like fatty liver or something. So I think that's why people are more growing attention towards the plants.
Exactly. So what she's mentioning, one of the another biggest reason people think that the meat-based proteins or meat in general perhaps not so healthier if you continuously eat meat. That means every day you eat red meat, perhaps you have a problem, because there are many studies confirms that that's again a debatable topic according to me, but still they confirm that if you eat meat continuously, you have cardiovascular diseases, increasing the cholesterol, and other diseases are associated with high meat consumption. However, the plant-based food consumption have a reduced health risks. So that's the reason why there is a trend towards plant-based and alternative. I think you have covered most of the things I really wanted to tell. So you guys are very clever, right? Super. So I have written the points here. Just go through that one. These are the actual major region. If you do the consumer survey around the world, everybody says the same thing. I want to be healthier. I want to have a less carbon footprint. I want to save animals. I don't want to kill them. And these are the reasons why they go for most plant-based or alternatives in general. Okay. And now there is also a good belief among the audience that among the consumers that we have a good technological innovations. Earlier it was a problem because usually the plant-based purified proteins are not so tasty, because they have this bitterness and they have this feeling in the mouth that astringency, the dryness feeling and so on. If, as I said yesterday, if they do not taste good, nobody gonna buy that one. But today the technology is going so fast, especially in food science, we are creating proteins that is more, I mean, they have a bland taste, means there is no taste in principle the protein should not have any taste to use it in a food ingredient, because the taste comes in the later stage. We add some other ingredient to get the taste. So we are doing some technological innovations to make, to remove these unwanted compounds, right? There are new technologies to create new kinds of foods. For example, we have 3D printing. Just to give an example, you can create jalebis with the protein ingredient with the 3D printing, right? You can create the foods that children like using 3D printing. There's a lot of technological innovations today, and that is actually helping us to have this plant-based in our daily plate. For example, the best example is we have milk-based, plant-based milk in the supermarket. We have meat analogs in the supermarket already. I'll show you so many pictures later. It's already in the market because that's a technology we use. For example, extrusion. I'm going to talk about that in next after a couple of lectures. We can create the fibrous structure. It looks very like a meat in your mouth. It's all coming because of that food science and technology, right? And because of this reason, there is actually increased tendency to consume alternatives. Make sense? All right, so I will just keep, I have already mentioned this one, and this is the trend. You can see that where are we heading, and we are here around 90, and we are going to reach in 2034 about two-folds, around 200 or 220 million US dollars. That's the billion US dollars. That's the market of the alternative. That's a predicted one. But what I wanted to mention that the trend is in this direction. It's not in this direction. Okay, it's going up and up. That's really good. Okay. Now, if you look into that, who are the largest consumers of alternatives? Again, it's the North America, Canada, and the USA. They are the biggest, the largest consumers and also producers of plant-based or alternative proteins and protein-based ingredients and product. And then there is actually Australia, which is Oceania region. They're also a good market. And India and China and this Asian continent here, they are also in higher trend. But if you look into the South America and African continent and some part of Europe, is like yes or no kind of thing. Okay. I really wanted to show some pictures now. I think 2024, that was the last year, or 2023. Before last year, I visited America to see their way of consuming plant-based or alternative proteins, and where are they. So we placed a visit to California, and we visited a number of companies that is producing plant-based alternatives, and I also visited a lot of supermarkets there to see what are they selling there. And beautiful thing that they are actually having a huge variety of plant-based alternatives. Just to give a shelf here, you can see that this is the alternative milk-based products, yogurt, plant-based milk. There's a you can have number of varieties. There's a tons of varieties of milk, plant-based milk you can buy there. I don't think in Indian supermarket we can get so many varieties today. I hope it will come in next 5, 10 years. I don't know. But America is already there. One more picture here is that this is the alternative meat, and you have alternative chicken, and you have alternative burger patties, and this is called tacos. Everything is available. And this is the, you can see that it's chicken breast piece. It is very similar, like in terms of its look, in terms of its texture, it was fantastic. We also tasted some food in the supermarket. They could cook and give us, and it was tasting also really good. And this is alternate. Some people who like eggs, so you have alternative eggs using the soy proteins actually. And this is the beef burger patties. You know, if you go to McDonald's, you get a burger, and those patties again they can be made from plant-based here. And I think this is, can you see shrimps here? So this is and you can also see that red color layer on the shrimp. They could really mimic is like a very shrimpy texture and color, and you know, also that bend shape of the shrimp, they could make it. And it also has a good amount of proteins and so on. And I could also take this is of course all the picture was taken by me. I don't have any copyright. So this is a coconut yogurt. But one of the things I found that there's a lot of cheese and yogurt and something, but they were all filled with fat, not much with proteins. That's the biggest challenge, I would say. They had a lot of coconut or other fat in the cheese especially. But usually the real cheese, let's say paneer in our case, it contains a lot of proteins, less fat. No, it has a fat, but protein is a major portion. But in this case, fat is the major portion. That's a problem. And this is burgers, and in Europe and in Americas we eat a lot of this salmon. It's the most consumed fish, and we could also get salmon slices, which is purely plant-based. And I opened this packet, and I could cook there in the supermarket. They helped us to cook, and it basically had a very fishy flavor, but the taste was not good. I don't know today. I don't want to talk about it's recorded. I don't want to talk about this company, but the taste, I did not personally like the taste, but the flavor, the smell was really good, very fishy. But now they're trying to improve. Perhaps everybody's trying to improve the quality of their food product. I'm talking about in 2023. So these are the examples to show that at least in the US market you find a lot of varieties already now, and people are consuming it. It's sold that much means they are consuming it. And then I also saw one. We went to another supermarket. In one of the supermarket, what they did was they actually had a separate plant-based section. You have a meat section, normal meat, dairy section, normal dairy, and you have a plant section, means there is only plant-based were put. And we went to another supermarket, and there they have actually mixed them. So you have a true meat and meat analogs. We have true milk and milk analogs, or plant-based milk. They all mixed it. We asked them, why did you do that one? Why can't you make it in a separate shelf? And then they say that, okay, the people who wanted to buy the meat one, now you directly see in front of your eyes the alternative. Now you probably pick that one. So that was a consumer, just to approach the consumer. So there is a huge, research on also how we market the plant-based products. It's not, if you make a separate section, basically the meat consumers, I won't go that side at all. It's not my thing. But if you mix them, perhaps, okay, right, maybe I heard a lecture about plant-based. Oh, there's already a plant-based here. Maybe I'll try this today. They would grab that and come back. Oh, it tastes good. I'll buy it again. So this is how the tendency, the trend will change. Does that make sense? All right, so now I'm going to talk a little bit about the business landscape. This is one example from this particular paper. They talk about the pea protein here, but it's the same thing for most of the plant and microalgal, whatever the proteins we're talking about. The trend is the same. We should start from the breeding here. So that I was mentioning that if you want to have high yielding varieties, you should change the breeding policies. Then it's farming, means what kind of fertilizers you use and what kind of environment you create for the plant to grow. And then there is a huge research on protein extraction that we're going to cover in my next lecture. Then about manufacturing, that means once you create the ingredients, you can't eat ingredients, you have to create cookies out of them, infant formula out of them, burgers out of them. Then there's a manufacturing industries, and then there is a selling industry. You produce something, then somebody has to sell it, and then the end day there's a consumer. It's a market trend. So it starts from the scratch where you start growing until you consume. There's a lot of market for this one. Somebody was talking about the startups yesterday with me, and I don't know where you place it yourself. It is not possible to cover entire value chain here. Maybe you are here, maybe you are here. Think about your interest in this particular value chain and you can have a startup. I'm telling about startup because actually this is one of the biggest opportunities today to have a startup, alternative business. So these are the major players in the I think it's in the US if I'm not wrong. For example, Beyond Might is a US one. So different companies are already involved in different different sectors of this value chain. Okay. So I don't know your interest for the future. If you want to have a business or if you want to join a company, find it where you fit the most. Okay. And just to showcase here, there is a lot of big companies already that are into the plant-based market. I hope you know some of them, and there is a lot of other. This is Corn. This is basically the mycoproteins company, and Impossible Burger. Have you heard about it? This is one of the most sold plant-based meat analogs in the US, and they don't yet have market in the EU, if I'm not wrong. I'm not very sure. And remember that it's not about only the companies and startups. The most important thing is the regulatory bodies, because they control the production, processing, and also consumption, basically in the sense that you can't sell everything to everybody. There is somebody to control that one. For example, in India we have FSSAI. I have no idea the full form. Food. Exactly that one. Okay, I'm sorry about that one. And US you have FDA, and you have WHO in the UN nation, and the European thing is controlled by EFSA, European Food Safety Authority, and every local government has their own food safety authorities. Often FDA and EFSA make most critical evaluation about alternative proteins, and then basically they start giving the guidelines, and then it comes to market. Please note that it's not an easy way to get things to the market. We are talking about years, not about months. For example, when they produce this corn, I think they took 12 or 10 years of research. When they identified the strain until it comes to market took 12 years or something like that, 10 to 12 years. It's not quickly something will come to market because you have to do a lot of safety studies and so on. Just to highlight here that the market is again growing. Some companies have seen the rise in the double, triple, and so on. I can skip this because I already mentioned to these slides. Now it's about cost. When you say to produce a plant-based or an alternative, about 20% will go for the ingredients that you need, and then logistics about 5%, and research and development is 15%, because there is a different sectors you have to improve to get the high quality food products. So this is just a rough estimate. Okay, and that's all about markets and consumer acceptability of plant-based or alternative proteins. Did you understand something? I was a little bit quick. I wanted to be a little bit quick to considering the remaining lectures. But was I very fast? You got the point, right? Okay, let's try to summarize what did we learn in this particular lecture. Okay, so we learned that there is actually increasing tendency for consumption and production and consumption of plant-based or alternative proteins. Do you agree? That's what the chart clearly shows, that It says that now we are at the business of $90 billion, we might reach to $200, $250 billion in next 20-25 years. That means that's a sharp rise, and statistics says that in most countries it's rising around 10 to 16% rise every year, 10 to 16% rise we have, that's the statistics, okay. And the most consumed alternative proteins is insect? No. What is that? Soy proteins or plant based proteins are the most consumed alternative proteins, but there is a tendency towards microalgal and mycoproteins and so on, and also cultured meat in the future, okay. And United States is one of the largest producers and processors of alternative proteins, and there is a big market there, and also in the EU and some part of Asia and also Australia, okay. And there is a lot of companies already established for production, processing, marketing, consumption, and many aspects of alternative products. There is a lot of companies, and if you really want to have a startup, I really recommend that there is a business here for you for the future, but you have to find out what is unique in your business. There is a lot of competitors for you already, a lot of startups. We visited more than 20 startups when we were in the US for alternative proteins. I also knew that in India also there is a lot of startups on alternative proteins. It is not something new for Indian context also, okay. To summarize, the market is growing and consumers are there, but consumers really consume it because they want to save the environment, they want to save themselves, they want to save the animals. That is the three governing reasons why the consumers are leaning towards alternatives. Does that make sense? Okay. Any question? Yes. We will take a break after a couple of questions here. We will take 10 minutes break, okay?
When we talk about alternative protein-based products, does not this have a lot of preservatives, emulsifying agents? Because protein, natural proteins, egg proteins or any other proteins has this emulsification, or any other, we don't have to, we have to froze them in the deep freezer. But when we talk about this, does not it creating another one industry to bloom, like additive industry, lot of preservatives to be added to mimic the characteristics or the sensorial properties? Just now you mentioned them, some fish has been, flavor has been added in the plant salmon, where it is not naturally present.
No.
So are we not blooming, or are we not rising the other problems along with the alternative proteins, although it is sustainable?
Yeah.
But it is an increasing trend, means we are unnecessarily taking lot of other preservatives and additives.
Yes, I think it's one of the important questions for debate as well, right? And what she is raising the concern that okay, we are creating alternative proteins, but the protein themselves are not edible directly. We need to create some structures, we need to create some flavors out of them by adding some other XYZ ingredients. Basically, if you look into the alternative food matrix, maybe they are having a bunch of ingredients there, and maybe we want proteins, but we can't eat proteins directly, and the ingredients are improving their stability, flavor properties and textures and so on. And her question is that, are we damaging things here? Do they have some environmental footprint, and is it creating some new markets? That was the question. It's actually the debate we are doing at the moment. There is a problem, I completely agree. I recently got a project from the Danish ministry, about 6-7 million Danish krone, just to investigate how some of the ingredients we add to the plant-based foods actually damaging the proteins and creating some unwanted molecules, and probably they have a potential effect on our health. I'm particularly investigating how that affects the human brain and the digestive systems and so on. It's actually something not very well investigated. It's a valid point actually. The biggest challenge today is that the food industries are more thinking about flavor and texture because they want to market. Flavor and texture is extremely important to sell the product. However, I don't say they're less concerned, but there is a less research on the toxicology. There's a less research on the nutritional unwanted benefits of this plant-based or other alternatives. There's a less research on, let's say, allergenicity that they are creating. So it's actually an area that we need to dig deeper into. It's very difficult to give a right answer and wrong answer, in the sense we don't know. That's the right answer I would like to say. The ingredients definitely help. I completely tell you that without food processing, no food can be sold. please keep it one thing in mind. There's always something running in among the consumers that, oh, processing is bad, ingredients are bad. No, that's not true. We need to process the food. That's a part of any food. You cook, right? It's very rare that you eat something raw, except vegetables and fruits. Most of the things are cooked. There is always processing. Food has to be processed, because when you process, you can store it for a long period. Nobody can eat food just you cook and eat in 5-10 minutes. No, it's not possible. They want to put it in the supermarket. The consumer has to finish his job and come in the evening, and then you have to grab it from the supermarket. It has to be stored. So then if you want to store it, you have to add preservatives. It's a part of the game. I don't say everything is bad, ingredients are bad, but the question is to what proportion they are damaging, the benefit versus harm. You need to find that balance. Research is going on. There is no right answer here at the moment. Hope I answered. You already perhaps have answer to this question. So it's actually a debatable thing.
One thing I want to add.
Yeah.
That there is rise of products with the clean label ingredient.
Yeah.
So because many of the companies or the regulatory body have taken this point into consideration, that the addition of the additives is nowadays creating a means that risk to human health, which is unknown and unaware, and it's not that experimented.
Yes.
Well documented in the
Yes.
literature.
Yeah.
But nowadays what the regulations are doing, that they are promoting or they are making the regulations or rules for those products which will be clean labeled ingredient.
Yeah.
Right, means the ingredient which has been used in the manufacturing of that particular product,
Yeah.
that has not been means that is sustainable,
Yeah.
that has not created any cruelty to the environment and
Yeah.
the animal as
Animal
well.
lives. Yeah.
There are some acts related to this, and
Yeah.
they are going on. Means there is research and development going
Development
on.
in that particular area. But yeah, that's a valid point here. Is I think in my personal, it's my opinion. I don't talk it as a scientist. I personally don't believe that the processing is, according to me, good. You need to process to a certain extent everything, because unprocessed food are actually sometimes dangerous, because we process, we ferment it, we germinate it, we cook it, we boil it. It's all the part of food processing basically. If you don't do that, you basically damage things and your body. And then ingredients, sometimes we need to add some ingredients. I know the biggest challenge is that when you look into the plant-based, the ingredient list, the number of E numbers is a lot, and lot of too many things, emulsifier, lecithin, that, this, too many things they're adding. But the question is, are they really bad? And I don't think there is a lot of research in that particular area to say. But the one thing I want to mention to you as scientists, that don't believe in 1 or 2 research articles that say this is bad, because they are actually focusing on one particular organism, one particular food product, one particular study. We need to read a lot of articles and make a consolidated knowledge. We need to have these random controlled studies. We need to have an epidemiological study. We need to take thousands of people in the population to find out there is really an effect or not. Unless and until it's very difficult to say it's dangerous, it's bad. No. We are in that particular stage at the moment. More research is going on, maybe more evidence will come. Maybe the clean labeling is the future. I don't know, but there is something going on. I fully agree. Yeah.
What's the need to extract proteins from alternatives, from alternate sources, as they are edible? Most of these grains are edible as such.
Yeah.
Why we need to extract it to add more price on them?
Good question. What he's telling that you can cook dal and eat dal curry, dal rice. Why you want to get proteins from dal and make a meat analog out of it, then eat along with the rice? That is his question. Valid question. That's also my personal question. However, human tongue is a different thing. Everybody have a different perception. I believe in environment, but not necessarily my father. My father really wants to eat fish, right? Then I can't tell him that, okay, you don't eat fish, it's environmental. Let's say chicken. I just give an example. He likes chicken. I cannot say them, okay, you stop eating chicken. He would say, okay, I'll stop eating chicken, but I really want to get the chickeny thing in my mouth at least once a week. This is a human's feeling, tongue, right? I really have a feeling basically. If I don't eat non-veg 1 week, I really feel that today I want to eat chicken, that feeling, right? But to satisfy that, we need to create an ingredient. That's a big market, that's a big business, because food is not just food, it's also market, business, and everything is located. A lot of employment is also is located with this one. So, considering the different market, different consumer lifestyle, basically it's important to have a variety of foods, and that's the reason why the ingredients are needed. For example, let's take an infant formula just to give an example. Every baby cannot drink the breast milk, right? Every baby is not possible. You need to have an infant formula with powders, proteins powder, lactose inside it, with a lot of minerals, a lot of fat and so on. How do we get that one? Okay, we have milk. Now I say that milk is bad, then you need to look for an alternative. Maybe use soy, maybe you infect, maybe use microalgae, I don't know. We need that product. So actually there is some need to get products rather than the whole food. And there it's important to get the ingredients out, basically the proteins out of a given matrix. And ingredients will give you a different functionality. She was talking about emulsification. You don't get a good emulsification if you take pea flour compared to pea protein isolate. And there basically the getting things out of them is very important. However, I fully agree, if we believe that I don't care about my taste, my perception, I just care about environment, then I strongly agree that we should not do any processing, try to eat whole food, in the sense that less processing or no processing, minimally processed food, that's really important. I fully agree. And there the local sourcing, local food culture, everything matters. It's a good question, but very difficult to apply for the whole world, to be frank.
Are plant proteins really cheap?
That's a good question. So I deleted that slide actually, considering the time. Plant proteins are cheap in some cases. For example, if I'm not wrong, soy protein concentrates are not that expensive. They are available in bulk. Some specialized plant proteins are a bit expensive, but the plant products, we went to US, I'm telling, I was checking the price. Actually, they are really equally priced. In some cases, they are maybe 20% higher than the the animal-based food products, but in many cases, they are equally priced. I think several years ago, basically, they were twofold higher than the animal or milk-based products, but now they are actually somewhere equal. I give one example. I think you know IKEA is a furniture store. It's a Scandinavian furniture store. It's also in India now. IKEA actually sells food actually in their restaurant. And there was an IKEA guy who gave a talk in our university, and he mentioned to us that they have a plant-based sausages, and they also have a normal meat sausage. They said that okay, maybe it's a little bit expensive to produce, but they actually kept the same price, or sometimes lower price, just to promote the consumers. But it actually worked out really well. And it's also important that when you start consuming more and more, things become cheaper. Just to take a TV as an example, 30 years ago TV was costing so expensive, but now TV is damn cheap. Mobile phone, so expensive, now it's damn cheap. Things will also change. It's more about the demand and supply, and the price will go down. But the biggest challenge is, I can tell you one more challenge, it might have a problem with some part of the world. I can give one example. We make idli with urud dal, just to say. But urud dal is a bit expensive. Now imagine I send all urud dal to Europe or America to create protein ingredients. Urud dal becomes super expensive in India, and our local people will have a problem. I can give a example of the mango. The best mango I can get in the Europe, not in my hometown, right? This just exported, and there is actually a problem. These things has to be politically investigated. I don't want to talk about that in the camera, but there is a problem, and there's a good side and the bad side.
Plant proteins, when we extract them, they do not have requisite this solubility.
Yeah.
Their solubility is too low. They cannot be employed in any case or any application.
Yes.
So for that we do modification by
Yes.
using different techniques, but modification is too expensive.
Yes.
So when we add any modification, then they becomes more costlier than traditional proteins or animal proteins.
Yeah, good question. However, there is already a sustainable, the LCA calculation, life cycle assessment calculations. They consider everything starting from the production until the consumption. If you make this LCA calculation, there is a clear evidence clearly shows that even if you do a number of processing, still plant-based proteins are much environmentally friendly compared to animals, even if you modify them, because their production itself has a lower carbon footprint compared to plant-based. When you sum everything, it's still sustainable. I know it's more expensive in this processing and other things, but if you consider things as a whole, it's still a minor part.
available related the traces while we extract proteins.
Yeah.
Related the traces present in the protein isolates or protein concentrates.
Yeah.
So there is no, I think there is very less literature available.
True, true. Yeah, I think this is something people are actually now considering, that's so-called, I mentioned just now, LCA calculation, life cycle assessment, cost calculation, energy input, everything is being done at the moment slowly to find out how much energy we need to do the processing, how much carbon footprint you have if you just to crush, if you just to add hexane to extract oil, what is the problem, everything is being considered, but I fully agree with you that the literature is bit less, but I see emerging evidence to show the carbon footprint for the plant-based protein processing. There are some papers at the moment. Yeah.
Phenolics, if they are present, they are. Someone told that phenolics are good, but they are not good in every case. Sometimes they attach with proteins, they make their digestibility very less.
Yes.
So we can, although we consume it, but they are not digestible as such.
Absolutely, so I will cover these topics. It's a good question. In the next coming slides, I have exactly those points. I'll talk about extraction, good thing and bad thing of the extractions and so on, and the digestibility concerns. Okay. Let's take a break now. Let's take a 15 minutes break and we come back again at 10:45. Would that be okay? I'm already delayed by half an hour, but there was a fantastic discussion. So yeah, okay. 15 minutes break and we resume 10:45. Don't sit in the classroom. Just go outside and take fresh air and come back. Stretch yourself, please. Okay, welcome back, and we're going to go towards lecture number 3 today and now, and that's about techniques for protein extraction, a particular focus on conventional extraction methods. Okay, we have been discussing about, just to follow up on his question, why do we need ingredients? And I answered that ingredients are very important to create new foods, new flavors, new textures. And if you want to get new flavors, new textures and new this one, we need to extract proteins from the biomass. We need to extract proteins from seeds, we need to extract proteins from insects, we need to extract protein from microalgae. So extraction is very important. By definition, extraction is nothing but the protein is located inside and you have to remove it from inside to outside. It's a simple definition, that's called extraction. Okay, we're gonna talk a little bit about different technologies that we use today to extract plant proteins or microalgal proteins or insect proteins and so on. All right. I will cover certain fundamentals now. I hope you, oh sorry, there is nothing on the screen. Yeah, there is a technical glitch and we are not getting something on the screen. Just wait for a minute for the YouTube viewers. Yeah. All right, now it's on screen. So, do you remember this structure? In primary school, that was the structure. Not primary school, maybe in the high school, we need to draw this one, and that would carry 5 marks. So, shading and I still remember my life at that time. So, it was a nice picture to draw. So, it's a structure of a plant cell, right? You know that plant cell, it's a lot of organelles here, right? I just want to cover again, I don't want to teach you as a primary school or high school teacher here, but you remember that plant cell are covered by this wall. What do we call that one? Cell wall, right? It is an important part of plant cell because that will stabilize the structure of the plants and the cell. Otherwise, the cell will blast, and it's an architect that it is a wall that maintain the structure of plant cells, right? Animal cell does not have a cell wall, just to refresh your memory. And below the cell wall, you have a, what is that membrane called? Plasma membrane. Usually it is weak and easy to damage, but cell wall is very hard and difficult to damage. Keep that in mind, okay? And this is inside, we have cytoplasm and other organelles and so on. Just remember that there is something called ER, endoplasmic reticulum, okay? Endoplasmic reticulum is the organelle that produces proteins in most cases, okay? The rough endoplasmic reticulum is the one that produces proteins. Just keep that in your mind for now, okay? And there is something called vacuoles here, you see? The big open space, sometimes filled with gas and sometimes with something, and where some things are stored. Remember these two structures, okay? Now the proteins may be somewhere inside the cells here, next to the endoplasmic reticulum, and maybe inside in the vacuole, okay? And now let us see, this is a structure of, this is plant, and this is our microalgae, okay? Microalgae are very similar to plant but not the same. They are also sometimes, most of the microalgae except cyanobacteria are eukaryotic species. They have a true nucleus, and they also have a cell wall here. Can you see? Okay. Then they have this chloroplast, and then there is oil bodies, and there is proteins are located here. So take home message from this slide is microalgae and plants are surrounded by a very strong cell wall. Can you remember? And proteins are present inside the cell wall or inside the cell. Now the proteins are actually surrounded by a strong cell wall. Can you just remember that, keep that in your brain for now. Now I will show a little bit about the cell wall and its architecture. Cell wall is actually very strong because it has a very complex network of certain polysaccharides and sometimes some proteins, right? Plant cell wall is made up of cellulose, the most abundant biopolymer in the world, like it's a lot of cellulose, right? And it also contains hemicellulose, right? And sometimes it also contains pectin, right? These are the three polysaccharides that the plant cell wall is made up of. They are interlinked, cross-linked, and that gives a very strong, stable structure to the plant cell. That's why plants are so hard, because of this cellulose architecture. Make sense? Good. Now if you look into the one example of a microalgal cell wall, it's very complex. It varies from species to species, family to family. Just to give a generic cell wall structure here, they also contain cellulose, okay? They sometimes also contains pectin and other things, but sometimes they also contain alginates, other kind of polysaccharides. So microalgal cell walls are still more complex compared to plant cell wall, and sometimes they are too rigid. That means very difficult to break, right? Now in the previous slide we realized that the cell wall is present and the protein is inside the cell wall. Now I am telling about cell wall is very complex and difficult to break down, okay? Now let us see the human digestion system. Now I take a microalgae solution, okay? I tell that, okay, now I have created a food, contains a lot of proteins. This is my microalgae, and I tell them it is a protein content is 50%, okay? And I will give this person a glass of microalgae solution, and I tell that it contains 50% protein, and this solution is very rich in protein. Now you drink, you become healthy. So this person drinks this microalgae solution, right? Now let us take this microalgae as an example. The microalgae goes inside and it comes to your stomach, right? In the stomach, and before coming there is an salivary enzymes. In the stomach we have these proteases, pepsin and some lipases that digest the lipids, right? And when does the digestion occur according to you? How the digestion occurs? This is a breakdown, right? Now you have studied in your biochemistry classes lock and key model, right? enzymes always likes a substrate, and the reaction only happens when they bind, right. You have an enzyme and you have a substrate. They would need to contact each other, then only the reaction happens. Do you agree? Now, the microalgae is coming inside your stomach. This is your stomach and the microalgae, and the protein is inside, right. Enzymes are where? Outside in the stomach. Now, the proteins will be digested when, if and only if these enzymes, attack the proteins. Do you agree? Now, there is a problem. What is the problem? We have a cell wall is a problem. It is acting as a barrier, all right. Now, the enzymes actually cannot penetrate through the cell wall to access the protein inside the cell. Now, we have a digestibility problem. Do you agree? Please note that plant cell wall is not permeable to most of the gastric proteases. Most of the plant, I am not telling all, but most of the plant cell wall are not permeable to gastric proteases, lipases and amylases. So, they cannot go inside because the pore size of the cell wall is very small compared to the size of the enzyme, and there is no active transporter to take them inside, right. But sometimes they go inside in rare cases, but in seed proteins, for example, it is very difficult for the enzymes to go outside to inside and then hydrolyze, right. Now, how do we solve this problem? That I answered the question of the cell. For example, we have cow, they have a special digestive system, that is why they eat grass and they can digest it through fermentation and so on, but we can't do that. We can't eat grass because it's a lot of cellulose. We don't have an enzyme called cellulase in our stomach to break down the cellulose. Our stomach is containing only amylases, proteases, no cellulases. So, we need to somehow open and then you give or chew it properly, break down the cell, and then you can make the protein accessible or digestible. Does that make sense? And there the processing becomes very important. I cannot feed them the whole microalgae here, maybe I need to unlock the cell and feed them only the proteins. Does that make sense? And where the extraction becomes super important. The conclusion is very simple. Plant cells, animals, microalgal cells are bound by a strong cell wall, proteins are inside, is sometimes very difficult to digest. So, we need to unlock, we need to open the cell wall, break the cell wall to make the protein accessible to the body, right. And there it comes the extraction becomes super important, and that also leads to the ingredient production. We gonna, any question in this part? Is it clear? Yeah.
Does it mean that we are consuming these cereals, they are not digestible at all?
Yeah, no, I don't say that one, because we cook it, we germinate it, and then we help damaging the cell wall. I'll come back to that one. Yeah, okay, raw, no, less digestible, I'm sure. Yeah, you need to ferment it, you need to germinate it, you have to cook it, you have to boil it, and all this process will damage cell wall, makes the protein more bioaccessible. That's another story, okay. But raw, no, raw ingredients, no, because of this problem.
So, that is also applicable to animals also.
Exactly, yeah.
Okay, thank you.
Now, I will talk a little bit more into exactly where the proteins are located in seed storage proteins. Now, I taught you yesterday that soybean is an important source of soy protein isolates, right. Now, this is the structure of soy seed, and if you cut it into half and you get this cotyledons, for example, okay. And then we have this place where the proteins are located. Now, this is a microscopic image. The proteins are located in a specialized structure called protein bodies, PB, okay, protein bodies, okay. And it is not spread throughout the structure, it is present in specialized locations as a protein bodies, okay. Now, we need to bring them out to get them as a protein ingredient, okay. Now, I will show a little bit more about how exactly the protein synthesis happens in the cells. Now, this is inside the seed in one of the structures you see. Basically, in one of the cells you have this endoplasmic reticulum, I showed in the plant cell, same thing, okay, and that synthesizes the proteins, Okay. Then immediately after synthesis of the protein, there may be this tertiary structure and quaternary structures can happen. That means the folding and everything happens next to the endoplasmic reticulum, right. And then the proteins, as protein bodies, they travel and then they will be located in a special structure called protein storage vacuoles. There will be small vacuoles here and the proteins are actually stored inside the vacuoles. Okay. The endoplasmic reticulum synthesizes the proteins and it is transported and located in the vacuoles, and everything is happening inside the seeds now, right. Now remember, the seed has seed coat and a lot of other barriers also here. Now we need to extract actually these proteins out. Okay. We need to extract these proteins out, and to extract these proteins out of the seed we need extraction technologies. Extraction technologies. Okay. So just to take home message is that remember, the seed and the proteins are not spread everywhere, it is present in a specialized places called vacuoles, and inside the vacuoles they are present as the protein bodies, and to get them out of the cells you need to damage the seed and get them out. Okay. So I can skip this slide, it is not so important. In case of microalgae, they do not have a specialized vacuoles to store the proteins compared to plants. Okay. They say that they are present in the chloroplast. This is chloroplast. So the proteins are located in chloroplast. Chloroplast, you know, right? The light harvesting pigment that helps in photosynthesis. Okay. And some people also say they are present in cytoplasm. I could not find a very good literature to prove that one, but it is expected that they do not have a specialized protein bodies in the microalgal cell. They are spread in the cytoplasm or in the chloroplast, especially in the in certain location of the chloroplast. What is it called, pyramid or something like that. Clear? So in plants we have a special protein bodies, in microalgae and other places they are just spread across, but cell wall is always present. Okay. Then we need to extract protein from inside to outside. Now I am going to show you how exactly we can extract protein from inside to outside. Protein is inside and protein is now outside using different extraction technologies. So that can be divided into two classification: conventional extraction methods and novel or emerging extraction methods. In case of conventional extraction methods, we have a dry fractionation, wet fractionation. In wet fractionation we have salt extraction and alkali extraction. In novel we have a lot of things, but I am only covering 3 of them today: ultrasound, pulsed electric field and enzymatic. It's just to show you classification. I am not covering 100%, but I am covering 80 most important ones today. Is it clear? So idea is to extract protein from inside to outside using different technologies. Okay. Each technologies have its own advantages and disadvantages, that is we are going to discuss today. What I am going to teach you is the principles of extraction, okay, advantages and disadvantages and some examples, that is it. You are welcome to ask me any number of questions in between. Alright. Let us begin with this one, the conventional extraction today. In the conventional extraction, one of the most common or the cheapest method is dry fractionation. Okay. I really found these figures from this article because that saved me a lot of time. They are fantastic figures, I just copy pasted here. Dry fractionation, basically as the word says, fractionating seeds based on the dry seeds without using any solvents. No solvents are involved, just using some methods, we just fractionating them. How do we do that? Just an example, you take pea here, okay, you take not fresh one, the dry pea, okay, and put it into the mill here. You have seen this mill, right, what we call to get the flour. It is very common in India, so mills are used to get the flours, right. Basically you mill them and you get the flour here, okay. Once you get the flour is now basically mixture of proteins, carbohydrates, small amount of fat and lot of other things, anti-nutrients and everything. Do you agree? There is no separation has taken place here. It's mixture of everything. Just think about wheat flour. It contains everything. But you are welcome to do the dehulling first. Just remove the seed coat first using the dehulling machine. Otherwise, usually the hull of the seed contains a lot of phenolic compounds, that's really nasty. So you first do the dehulling, and you're also welcome to remove the oil fraction using some solvent extraction or boiling and then re-drying. You can also remove that one. The idea is take the dry seed and then mill it, you get the flour. Once you get the flour, you do the air classification, that's a technology, and that will help you to separate protein fraction from the fiber or the starch fraction. Okay? So we have the flour, and then we do air classification, and then you get the protein fraction and carbohydrate fraction. Now I am going to show you what exactly we do it in the air classification. Basically, we supply this flour here, the what you got it from the milling, okay, and then there is actually a wheel that continuously rotates, creating the centrifugal force. Okay, a wheel continuously rotates, creating the centrifugal force, and we supply air in this direction. Okay, it's just a chamber. You're getting the feed, and there is something rotating here. Then you supply air in this direction. Now what happens is separation takes place because every particle has its own density. Do you agree? Its own size and its own density. Proteins are less denser than fibers and starch. Proteins are less denser than carbs, means fibers and starch. Okay. Now basically purely on the density based separation, you get a fine fraction which contains protein, and coarse fraction it usually contains carbs, which is starch and fibers. Okay. It's the most simple way of separating proteins, because proteins are less denser than the carbs. Is it clear? Okay. That is how you get the protein fraction and starch fraction separated from, especially from cereals. From legumes it is a little bit challenging. Why? Because it has fat. When you have fat, what happens? It just damages this principle, because this oily matrices changes the density of the proteins and carbohydrates because of the interaction. So, it is always recommended that you remove the fat before you do the air classification to get the best separation. Okay. Any question in the air classification? Yeah. Yeah, as fine as possible, but if you really want to talk about the size, I do not recall exactly. I think the fine particles here, what you get, the proteins around 303 micrometer, and coarse fraction, I think the starch fraction will around above 5 micrometer. That is the size we are separating. So, you as fine as possible, that is very important. Yeah, it's possible. There is a lot of pin mills, and there is a lot of milling technology today. So, I am not talking about extremely fine one, but it is actually still a coarse fractionation, but it is possible to mill as fine as possible. The property is purely on the density and the particle size.
Just like frictional properties, density is one, like gravimetric, frictional, mechanical property. Which property we are focusing in this separation?
Density. Purely on the particle size and density.
So, but if we increase this air in inlet, velocity of air inlet, then it will be difficult to separate the size.
That is exactly that I did not cover here. Basically, to control the separation, you need to control the velocity of this wheel here and the force of the air. These are the two controlling parameters that will change how you are getting this fraction and this fraction. I will talk a little bit about challenges as you may ask this question. Basically, I do not claim that you will 100% get proteins here, 100% you get carbohydrate. That is not possible. It is always this contains small amount of carbohydrate, this fraction contains small amount of carbohydrate, and this fraction contains small amount of protein. This is the biggest challenge, because I am not talking about pure based on the density. It is an impure, crude way of separating. This is one of the disadvantages of this particular method.
Sir, is there any role of aerodynamic properties of particles with this separation?
Could be, probably, I do not know. That could be. maybe it's not my area of expertise. I can't answer this question because I have no idea about aerodynamic properties of the particles. I never studied it myself and never read it myself with the intention. There could be, but what I know that this separates purely based on density and the particle size.
Sir, because whenever we separate anything with respect to velocity of air or with respect to air,
Yeah.
aerodynamic properties are important to separate them.
Could be, yeah, yeah.
If it is a combination of size and the velocity
Density
of air
and the aerodynamic property. I fully
that
agree with
could
you.
be the
Yeah.
reason for the separation of protein on the basis of size.
Could be, yeah, because of course I personally I don't have this engineering background, very difficult to give some explanation about the aerodynamics properties. You would be right. Let's read it about this point, okay? Good point.
Thank you, sir.
But what I know is that its density is very important, gravity basically, it changes and then you get the fraction. Is it clear? Air classification? Then sometimes they can also use this electrostatic separation. The phenomenon is very simple. When you supply this air inlet and the feed, basically there is a collision between the particles, okay? Particles collide each other and particle also collide to the wall of this instrument or the equipment, the barrel, right? Usually because of the collision between the particles, there will be charge transfer, and they say that the protein will get positively charged surface and the carbohydrates get, this is protein, and carbohydrates, let it starch, let us say, get negative charge on the surface because of the charge transfer reaction, and that will also help us to separate further. Now what they do is that when they are colliding each other, you get a charge, positive and negative. Then you have an electrodes here, cathode is positively charged and anode is negatively charged. This is positive in this case and negative in this case. Then you get the protein in this direction and the carbs in this direction. No, I am wrong. Carbs in this direction and protein in this direction. And based on the charge, they can be separated. This is another way of classifying using dry fractionation. Clear? I mean, I don't want to give a lot of explanation here. Just remember that because of the collision between the particles, the protein particles and the starch particles or the carbohydrate particles can get charge. Okay, they get a surface charge, and the charge could be positive on the proteins and negative on the carbohydrates usually. And it's very difficult to say how they get the charge. People say that the transfer of electron, that the transfer of ions. I could not find any strong evidence for that one, but everybody knows that the particles are actually charged. And based on the charge, you can actually separate them into different fractions. So you get a protein fraction here and you get a carb fraction. You have a question? Yeah.
Oil content.
Yeah.
But in case of press cakes, can we do it?
It's very difficult again. Basically what they do is that you do this hexane extraction first and remove most of the oil with the hexane extraction.
So after that it can be
and then it can be done, but it's always a challenging with basically you need to get a kind of a flowery matrix to do the air. If you have a lumps, it's always a challenge. So yeah, it works really well with cereals if I'm not wrong compared to legumes, but that is another disadvantages of this methods. Basically, if you really want to go with an air classification with oil containing matrices, you need to do a pre-treatment called de-oiling. And that's a very difficult process. Easy process if you would add an hexane as a solvent, but hexane is not environmental friendly solvent, and people talk about environmental footprint with hexane. Or you have to do boiling first, then you separate oil, and then you again you have to dry them. The drying is very energy consuming process in whole food processing. Drying consumes a lot of energy. So considering all these things is a bit difficult and challenging. It's not the best method in the world, however, it's really easy and energy saving method provided you have the right feed here. Any question? Yeah.
Sir, how we can extract these as proteins are macromolecules, how we can separate them from the micromolecules like other components which are with grains or which are attached with the flowers.
This is a good question.
What would be the percentage of purity? What
Yes.
would be the purity of that?
I will, that is one slide I clearly show how much percentage purity you get it. It's in the end of the slide. We are not talking about 90% purity and 80% purity, 100% purity here. No. Air classification cannot get 90% pure protein, impossible. This protein you get here is not 90%, maybe 40%, maybe 50%, maybe 60% depending on the type of the flour you have. and the impurities always anti-nutrients and phenolics and carbohydrates, everything will be present here, the remaining things. So, it is not the purification method, it is the fractionation method. Does that make sense? Yes. It's not a purification method, it's a fractionation method. If you really want to do 90%, you need to purify it again with other different technologies, which we will cover later. Make sense? Okay. It's just to separate, to get a rough fraction. Now, can you tell me, if this protein is useful somewhere?
Yeah, we can. So, it's rich in. Yes.
It is. Can you think about a food product where I can use this for this fraction?
Yeah, those foods which are good, which need a structure.
Yeah.
So we can add this protein resources.
Example? Do you have an example? There was a person you had. Fortified food, for example, you can use it in, let's say, baking, for example. We don't really need ultra pure proteins for baking, right? And there basically these kind of fractions can be used without any problem, because their sensorial properties, I'm not telling that you have to use 100% of this protein. They usually use 50-20% is replaced, the wheat is replaced by these alternative proteins. Okay? So this is not one of the advantages, very fast, less energy consuming. Disadvantage is that it does not produce pure proteins. You can't get protein isolates by air classification. Am I clear? Good. I need to go a little bit quickly. I already covered the advantages and disadvantages, but do you think any other disadvantage here that I did not cover? Any advantage or any disadvantage?
It is easy method. There is no use of solvents. There will be no impurity like a chemical impurity.
Exactly.
There are no environmental hazards of this method. And if we come to disadvantage, purity will be very less.
Yeah.
Anti-nutrients may be present.
Yeah.
And other non-nitrogenous components may also be attached with it.
Yes. Yes. So he has covered everything now. I don't want to explain this again. Is it clear? So, no solvents have been used unless you do de-oiling in the prior. Sometimes you need to use it, then it becomes expensive and less environmental friendly. Easy because you need a specialized person to do these things. Somebody will mill it, somebody will add it, somebody will classify it. It's very easy. You don't need a PhD for that. It can be done by anybody in principle. But the biggest challenge is the purity is very low. We are talking about 40, 50, 60% pure. Anti-nutrients will be very high because they always come together with this fine fraction, because they are also less denser. And impurity will be very, very high, because if you say 60% pure, the 40% could be impurities for us. Remember that if you have more carbohydrates, you will compromise the functional properties of the proteins, because you can't use it in every food systems. All right. Now, a little bit moving on to the salt extraction. This is also one of the common approaches to extract proteins. What do we do here is that, let's take pea again as an example. You mill it and you get the pea flour. Okay? Then the flour is suspended in a solution containing salt. It could be sodium chloride, right? And if you go back to my previous slide, previous lecture, I taught you some basics. You remember? Some proteins like salt soluble proteins, example globulins, and some proteins like water, albumins, and some protein like alcohol, prolamines. So every protein has some tendency tendency to dissolve in some site of solvents. Basically that principle is used here to extract proteins. Nothing difficult here. Some proteins like salt, they are solubilized, and some protein that does not like salt, they will be precipitated, right? Then you centrifuge, get a 2 fraction salt soluble protein and salt insoluble proteins, dry it and use it. That is the principle of salt extraction. Very easy, right? Of course, it has its own challenges, I will tell you later, but this is the basic principle. Clear? Purely depending on the solubility of protein in the salt solution. You can actually change the concentration of salt and you can selectively precipitate different kind of protein. That is also possible. That is the advantage of this technique. That I will explain over here. Now, this is actually a figure I copied from this particular research article. I think this is a protein from yeast, if I am not wrong. You can see this in the y axis. This is y axis solubility, x-axis the concentration of sodium chloride. The solubility was here increasing and then it decreased, right. The protein solubility increased, got the highest at when the concentration of sodium chloride is 1 molar, and then it started decreasing. Can anyone explain what is exactly happening here? Based on the charge, isoelectric point and charge, but we are not changing the pH here.
Groups.
Addition of OH
No,
groups,
H positive. In alkaline conditions, we are adding charge to it.
but I am not changing the pH at all here.
We are changing the concentration. The more H positive will be there, so there will be.
Okay, let's avoid this discussion. I tell you that the concentration of H plus and OH minus in this system is fixed. Let's say we are doing the extraction at pH 5.5, okay, where the protein is having one set of solubility. Just to avoid this discussion, what would be the other problem? Electrostatic attraction and repulsion is playing a role. That's a good point.
Na plus and Cl minus.
So sodium chloride has a charge, right? Na plus and Cl minus. Remember, as soon as you take a glass of water, take salt, stable salt, put it into the, and then you shake it, then the sodium chloride dissolves in water. When it dissolves in water, it gets Na plus and Cl minus. Okay. Now we have a beaker, okay, containing protein. This is protein, and it contains Na plus and Cl minus here, right. Now going back to my previous lecture, I told you proteins are charged. Did I say that one? Because of the amino acid, and somebody told it's amphoteric, right. Proteins can have positive charge, can have negative charge, and so on their surface, depending on the amino acid residues and the pH. Lysine can become positively charged, glutamic acid can become negatively charged, arginine can become positively charged, aspartic acid can become negatively charged. So they change their charging depending on the amino acid side chain and the pH of the solution. Now proteins are charged, right. Now you have another protein here, and that is also charged. Imagine, because of the charge they either attract or they repel, right. At isoelectric point they completely attract each other, they precipitate because the net charge is 0, right. At non-isoelectric point conditions, they are having different charges, they not necessarily attract, not necessarily repel, it varies. Is it clear? Now I add sodium chloride to this solution and it contains Na plus and Cl minus, right. And what this sodium chloride does, you have a sodium contains positively charged and you have negatively charged here, can you see? So that will shield here, and you have a positive charge on the surface and you get a chloride ion. Basically the protein charge is shielded, can you see here? And here also protein charge is shielded. Now since the charge of the proteins are shielded, protein-protein interaction is reduced. So protein interaction is reduced because of NaCl. Can you see? Because of the NaCl, the protein-protein interaction is reduced. Now the protein don't love each other, they just want to go away, but they start liking the water molecules. Okay. Now the protein will be completely hydrated. Hydration of protein is nothing but solubility of protein. Now the protein will directly go into water. Is that clear? And that's what exactly happening in this region. Okay. In this region, protein charge will be shielded by the positive and negative ions of the salt. So the protein-protein interaction is reduced, protein-water interaction is increased. Increasing protein-water interaction is nothing but solubility. So in this region, the solubility of the protein is increasing because of this reason. Okay. I should have not written in this part because my photo will come here. So, but is it clear? All right. Now we understood this part of the curve. Can someone explain what exactly happening here? Highest solubility.
Required to shield the protein is completed at
Exactly.
that concentration.
It's a critical point where we have a sufficient amount of NaCl which will completely shield excessive charge on the protein. Then the protein will really love water molecule and then solubilizes. Is it clear? Now, there is again a half of, this is a half of the answer for this question. There is a second half of this answer question. Can somebody explain what exactly happening here? Why the solubility is decreasing? But you still have more and more NaCl here. This protein is shielded, but why the solubility is reducing? Charge is again increasing, but what is the problem? What it will cause? Why you get a protein precipitation? Why protein is insoluble now? Increase in the total mass is not necessarily true.
Because of the repulsion
Because of the repulsion, what is being repelled?
by the disbalancing of the ions.
Okay. Semi-correct. Can anybody think why the solubility is decreasing here? Okay, I give a hint. Solubility is because of protein-water interaction. Okay, protein should love water if it wants to get solubilized in water, right? Solubility decreases when this interaction goes down. Now think about how this interaction is broken here in this particular part of the curve. Why we have a reduced protein water interaction and increased protein protein interaction in this region? Because of the saturation of the NaCl. That's the right answer. How and why? What exactly is doing?
More salt will be engaged with water.
Exactly. Now NaCl is start loving water rather than the protein, right? You are adding more and more NaCl, then there is another effect comes into play. That's called hydration of salt ions. Now NaCl is positively charged, right? Chloride ion is negatively charged, right? Of course, Na also likes protein, it also likes water, because you know that the water has two charges, right? You studied in your chemistry class, a delta positive and delta negative, right? Because of this oxygen molecule, right? Now Na plus likes the negative charge of the water molecule. So water molecule starts surrounding the Na like this one. Okay. Basically, the sodium ions and chloride ions are hydrated now more and more. Now these ions start pulling the waters towards them, and now the water is no longer available for the protein, and then protein cannot hydrate it, and they hate water molecule because they are not having water molecule any longer. They start loving each other and they precipitate. Is it clear? Okay. And this is the reason why the salt affecting, how it is affecting the solubility, and this region is called salting in, and this is called salting out. This is the two phenomenon you should remember if you are studying solubility in food science and technology, salting in and salting out. Is it clear? I have a nice explanation here again. In this region you have a salting in, and in this region you have salting out. In this region what is happening? Protein-protein interaction is reducing and protein-water interaction is increasing. This is protein, this is water. Okay? And basically it is because sodium ions are shielding the charges on the protein. They help protein water interaction, not protein protein interaction. But if you cross the threshold, then there is a more salt ions, and these ions will hydrate. They pull the water molecules towards them. So protein protein interaction increases and protein water interaction decreases, and the protein can precipitate. The solubility can decrease, and this is a phenomenon you can use to improve the solubility of your protein, plant proteins. He mentioned plant proteins are less soluble. You can make them more soluble by using salt at right concentration. That varies from protein to protein. Usually 1 molar sodium chloride is used in most cases. You will study literature article, they use 1 molar sodium chloride because that is often helps the solubility. Should I explain it again? Clear? This diagram is clear, right? I am sorry I made a big mess here, but hope you understood. Clear? All right. And there is something called Hofmeister series. It is a very well known series to just ignore this one. It is a very well known series to show the which kind of salt you can use. For example, if you really want to do the salting out, use this kind of ions. If you really want to do salting in, you can use this kind of ion. But in food science, we use sodium chloride and usually sodium chloride, because sodium chloride is food grade. You can also use ammonium sulfate to precipitate the protein. You can, I think ammonium sulfate is also food grade, you can buy them. Is it clear? Salt extraction. All right, now can you tell me some advantages and disadvantages here? Yes. Yeah. Yes. Yes, we
Is that
basically
the
have to do it either salting in and salting out, or both of them. It depends on what do you want. Basically, protein will start separating here depending on the salt concentration. Some will precipitate here and some will precipitate here and some will precipitate here, and then you basically try adjusting the salt ionic strength of the solution, then you can selectively start precipitating. That is possible, but basically you need to do both salting and salting out, but you can only use salting in. That is also possible. How? Let us look here. If you do only salting in here, basically all the salt soluble will be in the solution, and whichever completely hates the salt will just pellet off here, and that is the reason you centrifuge and you just get rid of them. If you do the salting out, first you do the centrifugation, remove the insoluble part, and then you do salting out and you get the fraction with the, that is dissolved here. It depends upon what you want to do. It's a, yeah. Yeah.
Should be again energy.
Yes, exactly, and these are the disadvantages we can discuss here. So what would be the biggest disadvantage of this salt extraction? What is the biggest disadvantage of salt extraction? My answer is already in my question. Presence of salt is the biggest disadvantage. After doing all these things, I said that okay, you go for spray drying or freeze drying here, right? Can you go directly? No, because your supernatant has a lot of salt now. Basically what you get here in the dry fraction is basically protein plus some anti-nutrient and other things, not 100% pure again here, plus salt. Nobody likes sodium chloride today, right? BP, blood pressure. So we do not want to have a lot of salt. Of course, the taste is a problem. Another thing is we really want to get rid of almost all sodium ions. It is not good in the food system, right? So you need to do one more experiment here. What is called? Dialysis, an extra step to get rid of salt. Unless you do salting out, but again there is a salt. It's not easy process. So you need to do dialysis or membrane filtration to get rid of salt here, and that is an added experiment to do. That is one of the biggest disadvantage. Easiest is advantage is, what's the advantage? Easily available. Sodium chloride is one of the cheapest thing to buy in the market, right? The cheapest even today is sodium chloride. Salt is cheaper. You don't need ultra pure salt here. Normal salt will do the job, right? So this is the advantage, this is the disadvantage. But please note that this method again does not give you the ultra pure protein. The protein concentration can be as high as 80% in some cases, depending on your raw material. Depending on your raw material, you can get the high purity protein. It's usually better than the dry fractionation. All right. So people often combine both dry fractionation and wet extraction together. It's a win-win approach, because in the dry fractionation you get the fine fraction rich in proteins, right? Use this fraction in the salt extraction. Basically here you get around 60% purity, and do the salt extraction, the purity can become maybe 80% here. If you only start without this one, the purity can be 70% here. So basically you can combine two techniques together to get little bit higher purity protein, and that is often done actually in the industries. They do not do one extraction, they often combine two extraction depending on what do you need at the end of the day. Am I clear? So this is often used, combination of dry fractionation and this one. People call it as mild fractionation, gentle fractionation and so on for this technique. Yes, I just need some water. Okay. Another important technique today that we are going to discuss is alkali extraction. I am pretty sure you have read about this a lot, and this is one of the most common used technique to get plant proteins microalgal proteins, insect proteins and so on. Okay. Alkali extraction, industrially followed, can be scaled up, extremely well investigated, can be produce things in very bulk, high quantities. Okay. So, this is the most used approaches to produce plant protein isolates today, okay, compared to salt and compared to other extraction method I have used. Now, let us talk a little bit about alkali extraction. The process starts exactly the same thing. You get the flour of given matrix, it could be pea, it could be soy, whatever it is. You are welcome to do de-oiling. Please note that I do not mention de-oiling here, you are welcome to do de-oiling if you really necessary, especially for oil crops, oil seeds. Okay. And then basically you dissolve them it in a solution containing sodium hydroxide or potassium hydroxide. These are often used. Sometimes people also use sodium bicarbonate. Sodium hydroxide can be food grade, right. We all know something that protein solubility changes depending on the pH, right. This is the curve I taught you last time, the basics of protein, I taught you this curve, right. Protein has a very good solubility at particular pH and the solubility drops, solubility completely lost here. What is that point called? PI, isoelectric point, and then if you increase the pH, the solubility increases, right. Now we have two regions where we have the high solubility, right. This is the basic principle of alkali extraction, high solubility and low solubility, both these aspects are used. Okay. Usually alkali condition here the solubility is actually maximum, can you see, compared to acid condition, alkali condition has a higher solubility. So, they use this phenomenon, they exploit this phenomenon, they adjust the pH between 8 to 11 you often, right, and when you adjust the pH 8 to 11, how do I get rid of this one? When you adjust the pH around 8 to 11, the most of the protein will be solubilized here, okay. Then what they do here, the centrifuge here, then the pellet contains insoluble fractions, it could be fiber, it could be hull matrix, it will be starch and what not. All this insoluble, alkali insoluble fraction will be precipitated off. So, you remove them by centrifugation, right. And then you have a supernatant here. What does that contain? Soluble proteins, okay. Then you remember the same curve here, the protein is soluble in this region, but the protein is insoluble in this region. Now what we can do? Precipitate by adding acid or HCl here, right. You add the HCl, bring the protein to its isoelectric point and the protein will be precipitated. So, now you get the tube containing protein precipitate and some water HCl here, right. Basically it is water because it is neutralized. Am I clear? So, basically you precipitate the protein here and again centrifuged, you got the protein fraction. Is it clear? We are purely using the solubility curve of the protein to extract the protein. We use both isoelectric point concept and the solubility concept here. Since usually alkali conditions is more preferable because that more solubility means what? More yield. Do you agree? You throw less here. More solubility means more yield, you throw less here in this particular part, and that is the reason why people do not use acid extraction. You are welcome to use acid extraction, I am not telling that you can't use it, you can use it, but the yield often lower compared to alkali extraction, alright. And then you precipitate them again by adjusting the pH to PI, then you get the protein out. Any question? No? Yes? Yes. Exactly, there is a lot of disadvantages here, that is for my next slides. I will get back to exactly the color problem and something. Good question, I will get back to you in detail. Sorry, I could not hear you. Equation. Oh no, you can always use this pH is equal to the pH and PI equation. What is it called? Anderson Hasselberg equation, right? pH and pi relationship, there is an equation. Yeah. Yeah, it's called, I can't pronounce that name, Anderson-Hasselbeck equation. That is showing the, basically when you have an pH becomes pi when then the acid form and the base form becomes equal. Then the net charge becomes 0. There is an Hasselberg-Handels equation. You can Google it. You'll find it. There's an equation. Yeah. 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 Yes. 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 Absolutely. Yeah. 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 No. No. I mean, basically protein has properties called denaturation. Basically they are, I remember tertiary structure and quaternary structure, they're beautifully folded, and that is actually governed by hydrogen bonding and hydrophobic interaction in addition to disulfide bond. Because of the alkali condition, they can open up, because you can even break the disulfide bond in alkali condition. Usually proteins have two properties. Sometimes denaturation is reversible, sometimes they are completely irreversible, depending on to what extent you are damaging. As soon as you remove the salt or the base and acid here, they can refold to certain extent, but sometimes you cannot. That is a balance. So remember, one thing is that we do not always need native protein structure in food applications. We do not need it always. It's okay to use denatured protein for food application, then application changes. Sometimes we really have to denature protein to improve the water holding capacity, oil holding capacity. It depends on the application. So food processing will always denature protein to a certain degree. It's difficult to maintain the nativity. The nativity is important when you want to use it as an enzyme, because then the quaternary structure and everything becomes super important. For protein, it is not necessarily if you want to use it for the food ingredients. Yeah.
Okay. One more point I want to just have a discussion on this, that during my PhD research work, I isolated the protein using acetone precipitation, and then further my supervisor said that you have to maintain the functionality, because we need to go for the correlation with the product quality.
Yeah.
At the end.
Yeah.
So I went for dialysis after
Yeah.
studying the literature, that by doing the dialysis against the acetic acid,
Yeah.
oxidation of the bonds will occur
Yeah.
during the dialysis process, and there may be some maintenance of the functional property of that protein
Yeah.
which I
Yeah.
extracted,
Yeah. Yeah.
and there will be further more purification also, because dialysis will remove the minerals in case they are being attached with the
Yeah.
proteins.
Yeah.
So what is the possible chemistry behind this? Because you said that your expertise is the protein oxidation.
Yeah. Yeah.
So
It's basically like, I mean, basically, let's say that this is protein which is three-dimensionally folded, and then you have a disulfide bonds here like this, right? And because of XYZ treatment, then they become like this or they become like this and so on, right? Basically, you denature proteins, the three-dimensionally folded will become open up. Now this one has one type of functionality and this one has another type of functionality. It depends what do you actually need in food application. It's not that, okay, native is the best in the world, not necessarily true. Maybe denature will give you the more functionality. So don't go with the myth that we need a native, but we need the native protein to understand the chemistry. I fully agree. It's the whole concept of our project, rape project, the 60 million one. We trying to get them as gentle as possible, as denatured, less denatured as possible, but just to understand the functionality. But we don't claim that, okay, denaturation will completely remove their functionality. It's not true. It depends upon what exactly you need at the end of the day. Maybe denatured is more digestible than the native one, you never know. So, but coming back to the chemistry point of view, basically I have the slides later. If you have more hydroxyl ion, basically you cleave this bond and you will denature it. And if you have more acid conditions, you protonate them and it will repel each other and you help, you break the hydrogen bonding, and then you open up the structure and then it will easily cleave this bond. There is a lot of chemistry going on. So one thing to keep in mind is that probably native is good, but may not be very functional. Denatured is maybe better, maybe it's bad also, it depending on the protein and the condition. But the problem here is that to denature you add lot of ingredients, NaCl, NaOH, and all these things have more effect, which I'll try to cover. Okay? Yeah.
Sir, why we need to extract protein? Suppose we are having 60% of protein percentage in, why not we go for the other component to extract, like carbohydrates are present there. We extract 40%, we will get 100% of protein. Why we need to extract protein only? Why not the other components which are minor compared to protein?
That's exactly what's happening in this particular step. Basically you're extracting protein in this, for example, you get a protein supernatant here. The pellet what you get here is actually containing the minor, the carbohydrates, fibers and so on. But the supernatant again contains polyphenols and all the soluble fractions.
Minor components. Suppose our sample contains 60% in dry fractionation.
Yeah.
It contains 60% of protein. There is 40% are another component,
Yes.
like fibers, or any other polysaccharides.
Yeah, yeah.
So why we do not go for the polysaccharides to extract? So we will get 100% of protein.
How do you extract polysaccharides?
There might be methods. There is one method we can go for, like enzymatic.
That's again extraction.
We can go for enzyme.
So what I'll come back to the enzyme. So whatever you say is again extraction. Is the focus point is different. What you are extracting? I'm telling I'm extracting proteins. Basically, you're also extracting carbohydrates. Do you agree with me? All the fibers are coming here. So I can tell mild fractionation for carbohydrate extraction. It's the same thing. It's basically the focus point is different. Basically, the process is different. But at the end of the day, it's extraction. I don't care what method you are using to get what, but at the end of the day, you're fractionating in different fractions. One fraction will have protein, other fraction will have carbohydrate, one fraction will have polyphenols. It's again extraction.
Yes. So it's simply this is a question. There is a minor percentage of another impurities.
So I'll get back to this point. The minor is actually a bad thing to use here. I can give you one example. Less than 1% of polyphenol on a protein can change the protein quality completely. It can make protein very brown, it can make protein bitter. Only less than 1% I'm talking about. So you have 99% pure protein. I can say, oh, I have a 99% protein, but nobody can use it, it's bitter. Can you buy that one? No. That's the reason why fractionation and purification becomes super important. One thing is, please note that fractionation is not necessarily good. Basically, you're also up concentrating in some cases unwanted things here. You're removing one thing, but you're also up concentrating another thing here. Continuously, you're concentrating polyphenols in the supernatant. Do you agree with me? Because polyphenols don't go in the pellet. They're soluble unless they're bound to the carbohydrate. So you're also up concentrating this fraction you get over here. Maybe it's rich in protein, maybe rich in anti-nutrients also. Then you need to again purify them in other technology, membrane filtration. Yeah, you have a point? Yeah.
I have a question, sir.
Yeah.
Actually, I have two questions.
Yeah.
First one with the extraction.
Yeah.
So after doing isoelectric precipitation,
Yeah.
there also the reaction happens and salt will be formed.
Yes, NaCl, exactly.
Yeah. And if we wash it multiple times,
Yeah.
so how sure are we that it's removed?
Yes, it's a good question. Basically, NaCl content will be there. It's actually a game, trial and error game. But there is definitely something, because usually the pH will govern the NaCl concentration. pH will overweigh, the isoelectric point will overweigh the salt concentration. So protein will precipitate. So it's possible. Yeah.
How sure are we that it is removed? That's my question.
Yeah. Again, you do the protein analysis. You take the fraction, go to the Geldahl's method, CHNS analysis, chromatography, I don't know, BC analysis, measure it. So that's the only way. All purely trial and error here. Okay. Once you optimize the process, and then it is industrially applied, because I know at this pH it will precipitate. I don't care about NaCl now, because still it precipitates. It all has to be optimized for individual protein, for individual matrix. It's not a universal method I'm talking about. Please note that. It's a universal method, it works, but this is not a universal method, but it works basically. This is universal thing. That is unique for each protein classes, right? Use that as a key factor to find out where do you want to precipitate. It's a trial and error. if it's new protein. Yeah, yeah,
One more question, sir.
yeah.
Actually, mine is a protein which is not much studied.
Yeah,
So I have extracted protein at pH 10
yeah,
and pH 12 as well.
Yeah.
I have found my isoelectric point at 3.6.
yes,
So when I did extraction at 10,
yeah,
it gave more pure protein,
yeah,
but the emulsifying capacity was less.
yeah,
When I extracted at 12, yield was more,
yeah,
purity was little bit compromised,
yeah,
but the emulsifying ability was much good.
yes.
So should I attribute this to the polyphenol content?
Yeah, you could be. I'll come back to that particular answer in next slide. Good question. Could be. Yes, you're right. Yeah, yeah. Shall I move? Continue. Any other question? I think it's a fantastic discussion. I'm pretty sure you're understanding what I'm teaching now. It's cool. So is it clear? Alkali extraction. Please note that it's most commonly used because it gives highest yield. Okay. I'll answer your questions along the way, and also your question about polyphenol and minor components. So this is one of the examples. It's our own study we published, I think, back in 2020. We're trying to extract proteins from hemp seed meal. Hemp, you know, right? It's also produced in India. We can see that increasing the NaCl, potassium hydroxide concentration, we increase the yield. Okay, and if you compare the yield with the salt extraction with the alkali extraction, you can see that the yield is maximum is around 30% here, where you go up to 80% here. So usually alkali extraction produces highest yield compared to salt extraction. It's not only in this study, a number of studies prove that one, and that's the reason why people go for alkali extraction compared to salt extraction. Please note that the protein profiles here could be different, because this will extract only one set of proteins and this will extract different sets of protein, and that's the reason why your functional properties also changes depending on the pH, because the solubility varies depending on the pH, right. At pH 12 you might extract more number of proteins, more diverse protein compared to pH 10, and basically remember, plant proteins are not a single protein, it's a mixture of hundreds of proteins. Each protein will have their own isoforms, their own proteoforms. There's a small difference in them, and their solubility is different depending on the salt concentration and the pH. So your functionality, what you're measuring, not for the individual protein, it's for the mixture. So the small change in the protein proportion in the mixture can change the protein quality or functionality. That's one of the answers. So that's the reason why the protein coming from the salt extraction can have a different functionality compared to alkali extraction. Alkali extraction at different pH can have a different functionality, because you are actually extracting different types of protein at different proportions. Okay. All right, and this is about the digestibility, except for the, this is from, I think it's from our department, this paper. I think it's from rapeseed, right? Can I read some rapeseed? Yes, exactly. This is from the rapeseed protein. You can clearly show that the salt extraction has a lower digestibility compared to alkali extraction, something like that. So the digestibility also varies depending on the which type of extraction you are using, because sometimes some extraction will denature the protein, then the enzymes can easily access to the protein, can be more digestible. So sometimes denaturation is good, sometimes it's bad for the functionality. So it depends what is your end goal. End goal is to have the highest water holding capacity, go for salt extraction, maybe, I don't know. End goal is to have a highest digestibility, I don't know, you have to go for salt or alkali extraction. It varies from protein to protein, materials to material. It's again a trial and error method. There is no universal extraction method that gives you the highest yield, highest digestibility, highest water holding capacity, no. You tweak it, you train your protein to get the best one, what you want. Make sense? And that's the reason why the plant-based world is so complicated. It's very complicated because of this, all these things affecting the end result. Okay. Coming back to your own point here, there was a study published a few years ago. They clearly shows that the water holding capacity and oil holding capacity is different depending on the extraction you're using. If you use AAF, NOH, they have a different solubility. If you use NOH together with salt, they have a different solubility, and their water holding and oil holding capacity is changing completely depending on what type of extraction you're using. It's clearly showing us that extraction actually matters a lot toward the functionality. So if you want a low water holding capacity, probably you have to use this method. If you want the highest one, probably you need to use this method, is this one. So, the methods matters, the extraction method matters to get the right functionality. Please remember, we do not have to use always the highest water holding capacity ones, it depending on where do you want to use this protein, make sense. So, there is no universal method to get everything as the best one, no, use the, you optimize it, you find out it and find the best one. There is a lot of room for exploratory research. All right, can you talk a little bit about the disadvantages here? One of the disadvantages he asked about, okay, what about the purity and what about the color and something like that. Let us talk a little bit about the disadvantage now, is it okay? I need some water. Yeah.
During the extraction method.
There is a lot of residual effect, there is a lot of other chemical reactions are going on because of the sodium hydroxide. Sodium hydroxide is a strong base. Bases catalyzes a lot of chemical reactions. You have studied in organic chemistry, right? Bases catalyzes a lot of chemical reactions and that can essentially damage proteins, that can essentially bring new chemical reaction into play. And that's something I'm going to explain in the next couple of slides, okay? The residual chemistry. One of the chemistry that brings the alkali extraction is, are you tired? I'm sure you're tired, don't say no. But I'll give you a break after this chemistry part, is it okay? I'll try to cover it as quickly as possible. Yeah, according to this YouTube thing, I have to give a break later, is it okay? But maybe you can stretch now, like, I'll give it 10 seconds to stretch. Is it okay? Stretch, no problem, stretch yourself. You stand up, everybody stand up. Everybody stand up, okay? And now you do like this. Yeah, and then like this, don't hit the person next to you, okay, and then now maybe like this, okay, and down, and if there is space like this, okay, and then you twist again, okay, okay, now you sit and breathe deep, take a deep breath and release. Deep breath again and release. Is it okay? You're fresh now, right? As in the morning, so good. Now we talk a little bit about chemistry, my favorite topic, and I'll take it in as slowly as possible, but I have to rush again. I don't go in detail, but ask questions if it's not clear, okay? Now we are talking about the residual chemistry that sodium hydroxide brings here. The first thing is that because of the sodium hydroxide, we create a new molecules in the system that's called lysinoalanine and lanthionine. We can also racemize the amino acids because of the alkali condition. Racemization is conversion of D to L form or L to D form. You know that the protein amino acids are always in L, but sometimes they can become D because of the OH minus ion, okay. The first one is the lysinoalanine and lanthionine formation. Because of the OH minus, you break the disulfide bond here, okay, and you release a new molecule that's called dehydroalanine. Dehydroalanine, okay, and the OH minus can also take this SH group from cysteine as hydrogen sulfide. Actually, hydrogen sulfide smells like a fart, right? Basically, if you do a lot of alkali treatment, your protein can smell like a rotten egg because of the hydrogen sulfide, and they release again the molecule called dehydroalanine. The serine residues can dehydrate, remove water molecule because of the OH minus, okay, and get the dehydroalanine. Now all this reaction end up with the product called dehydroalanine, right? If you carefully look into the structure of dehydroalanine, it has C double bond C, can you see? And the C double bond C is an electrophile, highly electrophilic in nature, right? Now the protein contains nucleophiles, can you see, amino groups, and the thiol groups. Where is thiol group? Okay, it's missing in this structure. Okay, I'm showing its only product. For example, cysteine has a thiol group, okay. Lysine has an amino group, right. So there is an electrophile here and there is a nucleophile here. Organic chemistry says what? there is a reaction. Electrophiles likes nucleophiles, nucleophiles likes electrophiles, they react, they make a covalent reaction. Basically, that will leads to the formation of protein cross links. Now we have a protein with lysine here, and the protein with cysteine here, and the protein with dehydroalanine here. Basically, they react each other, and then you get the protein cross links. A new cross link is formed. Can you see? Because of alkali treatment. And please note that this is not a peptide bond, it is just a simple covalent bond here, all right. Only peptide bonds can be cleaved in your stomach. Proteases can cleave peptide bonds, they can't cleave some other bonds. Now we created some other bonds, they can compromise the digestibility of the protein. Does that make sense? So because of the alkali treatment, we are creating the new structure. New structure means new functionality, that's a good thing or bad thing, but it can also compromise the digestibility of the protein. Make sense? It's one of the important chemical reaction often ignored because they don't know chemistry, this food science sometimes. They talk about functionality, so there is a chemistry is playing a role. Just to give some example here is that we have a method to analyze LAL and LAN formation in our department using LCMS. There is a paper I bought here, it clearly shows that increasing the LAL and LAN formation and then decreases here, right. So basically you get more and more LAN formation depending on the pH of the solution. It decreases later because it's not because they are not producing, it's basically the LAL and LAN can also degrade further, okay. So if you have high alkali condition, you can form more LAL, lysine-alanine, and also more LAN. This data is for LAL. Is it clear? And the same paper they published later the digestibility of that one. They show that the digestibility is also compromised because of the alkali treatment, because of the LAL and LAN formation. There is a compromised digestibility. Pepsin and trypsin cannot recognize LAL and LAN, and they can compromise the digestibility. And they also published, this is Chinese people, they published again showing that in the pepsin, this is pepsin and this is pepsin plus trypsin treatment, this is pepsin. They clearly show that the release of the LAL is only 8%. Can you see? That means that the proteases cannot release them from the protein. If you have a cross-linked proteins made up of LAL and let us say LAN, if you put protease enzyme into play, for example, pepsin and trypsin, they can't cleave this one, they can't cleave the peptides here, they can't be released significantly. In some cases only like less than 1%, and that actually compromises the digestibility. And nobody knows if you eat LAL and LAN what happens to your body. There is a new molecule, it is not an amino acid, it is an amino acid, but it is not a normal 20 amino acids we have, it is a new structure. If you continuously eat LAL and LAN, I have no idea what is the health effect of that one, less investigated. Is it clear? And the other thing is the D-amino acid formation. This is the most common form of amino acid in our food, Al, okay. Because of OH minus, basically you remove this proton as water molecule, right, chemistry. Then you get a carb anion formation here. So now if you consider it as a plane, so you remove, there was an hydrogen atom in this direction, and you remove that hydrogen atom, right, as a proton. Then the new proton coming can actually, now you lose the chirality, the new proton can come in this direction and also come in this other direction, right, and that will check the enantiomer, the racemization will happen. Now the L can become D. Please note that the D amino acids are different than the L amino, they look very similar, same molecular weight, everything is the same, but their functionality is different because our enzymes in our body apparently cannot recognize when there is a D. The bioavailability or the digestibility are compromised, and that some cases they are actually digested, they also go to the bloodstream, and then inside your body again the protein synthesis should occur, right, and then there may be mismatching happens and the functionality of the enzymes, muscle protein can be compromised. Is it clear? So we really have to avoid D. The D is very less investigated. So well, L, the body likes the L, the D, they might be not digestible at all, they might be digested, they might be bioavailable, they might also do the protein biosynthesis inside, but the functionality of that new protein in your body may be a different one. So, it is not a good molecule to have. However, there is no studies on this one. I could not find any single article, and we are going to publish one soon. Okay. Coming back to the color change, whenever you do the alkali extraction, you get this color. Have you seen it? Red, brown, what not, all this different color you get alkali extraction. And the product of the alkali treated protein is like this one, brown, green, yellowish, what not, different color you get. It simply because of the chemical reactions. Okay. In the previous stage here, I taught you that in this step, you actually precipitate the unwanted thing, and the supernatant contains the protein, right. It is not just protein, it also contains polyphenols, it also contains tannins, it also contains vitamins, what not, everything is present here, right. You are also up concentrating unwanted things, and polyphenols, tannins, anthocyanins, they have color. So, it is a pure protein solution we say, but not necessarily pure protein, it contains protein plus PP, polyphenols, tannins, what not. And if you dry it, freeze dry it, you get this one, you spray dry it, you get this one, because of this small amount of 1% of polyphenols, less than 1%. Why they become color? I have a chemistry here. This is the structure of a polyphenol. It has OH groups. Can you see? They are called polyphenols because they have an aromatic ring and a hydroxyl groups. When they have a catechol structure, the catechol is basically the one with this neighboring hydroxyl group, the catechol structure. They are readily oxidizable. You do not need sometime an enzyme, just pH can induce auto oxidation. Okay. You have alkali condition, and that will induce auto oxidation of polyphenol, and the polyphenol becomes quinones. Can you see? So, this structure became this structure, quinones. The quinones are colored, they are highly colored. Okay. Alkali conditions favors this reaction, and that is the reason why you get this color. Polyphenols themselves may not be very colored. It's the quinone forms of the polyphenols are colored, and the quinone form is actually favored by the alkali condition, and that is called polyphenol auto oxidation. But the reaction does not stop here. The quinone forms are highly electrophilic in nature, electrophilic, because you have a carbonyl group. Can you see? Carbonyls, you have studied that in your organic chemistry, they are highly electrophilic. Okay? And the proteins have nucleophilic groups, amines and thiols. Electrophiles loves nucleophiles, and they just react together to two pathways, Michael addition or condensation, shift base formation, addition reaction or condensation reaction from protein polyphenol adduct, a covalent compounds. Now, the protein what you have here are bound to polyphenols, right. Now, it is not a pure protein any longer, it is a protein bound to polyphenol, it is called protein polyphenol adduct, and their surface properties are now different, because originally the protein had cysteine group and lysine group, right. Now, I have a polyphenol attached to that one. Can you see? Now, the functionality, the solubility of this protein is entirely different, because the polyphenol brings the OH group on top of them. Makes sense? Sometimes the solubility increases, sometimes solubility decreases because of the extraction, could be because of this reason, because they are reacting with the polyphenols. And not only that, the digestibility of this one could be different, because enzymes might love them or enzymes might hate them, because polyphenols non-covalently can also interact with enzymes because of their aromatic benzene ring, because of their hydroxyl group they can make hydrogen bonding. They change the chemistry completely now, so they can compromise the digestibility. They might improve, they might decrease. There is a lot of studies on that one. Is it clear why you get the color? Basically, this product is actually colored. If there is a shift base formation on the protein, they are colored. Have you seen sunflower proteins? is green in color, right? Right, because of chlorogenic acid, and the protein reaction with chlorogenic acid gives a green adduct. So, sunflower extraction always get to green color protein because of this reaction. Does that make sense? So, conclusion here is that alkali treatment can oxidize polyphenols to quinones, and quinones themselves are colored. The reaction will not stop there. Quinones are highly electrophilic in nature. They react with the nucleophilic residues of the protein, lead to protein polyphenol adducts, and they themselves could also be colored, plus they can improve or decrease the protein solubility, they can increase or decrease protein digestibility, because they are a very new compound now. Did I answer your question? This reaction is done in only small amount of 1% polyphenol I am taking. Protein is a high molecular weight, polyphenol is small, but it is a low molecular weight, but still there is a lot of polyphenols present. Reaction can happen easily. So, this is the problem with the alkali conditions. Conclusion, coming back to your own questions, where do we get, what kind of yield you get? Here is some data. It is not a true one, I believe, it varies from the samples to sample, protein to protein, matrix to matrix, but this is something you can get it. Is it clear? Okay, let us try to conclude the extraction methods. Is there somebody to dare to conclude for me? I am tired. Who will conclude extraction? Yeah, try. Yeah, please try. Can somebody give her a mic? Yeah.
First, we start with the extraction method, that is conventional method, and in that we can go with the dry and wet method.
Yes.
Right. In dry method, we go for the milling.
Yes.
We have to convert the cake form into flour form, or the whole form pea form into flour form, and then we go for the either air classification or the isoelectric charge separation. Right. So after that, then we go for the extraction via the solvent.
Solvents, yes.
And in those solvent, we use Osborne fractionation method. Either we can go for the salt solutions extraction, or either we can go for the alkali solubilization method.
Yes.
And they both have their advantages and disadvantages. And to conclude, means after that, do I have to tell about the advantages or disadvantages?
Please go on. Yeah, it's your time now.
Okay. In salt one, we need to go with the determined level of the NaCl concentration.
Yeah.
And there might be chances of the residual of NaCl.
Yeah.
So we have to go for the further purification as well, in case we want to have the maximum concentration of the protein content.
Absolutely.
Right. And when we go with the alkali,
in salt concentration.
Why we use alkali? Because in case of acid and alkali comparison extraction method, the yield is higher and alkali is cheaply available.
Yes.
So that's why we prefer the alkali extraction method.
Yeah.
And and after that, the negative point of the alkali extraction method is that it may cause some unwanted reactions, which may result in the formation of unwanted compounds, the consumption of which is unknown to the health, human health.
Exactly.
And the overall means extraction yield is here. And to conclude that, alkali extraction method is best one preferred in case of conventional extraction method.
Yes.
So
well done.
all.
Very good conclusion. Claps for her. Yes. If you want to add more conclusion on top of that,
So I want to add one more thing, that she told that alkali extraction is better than other conventional methods.
In terms of yield.
Yeah, in terms of yield. But as per this health perspective, we should not use alkali extraction methods unless there is complete clear vision about the components present inside the material.
Exactly. The second part is very important. Unless you do not know, that's very important. I don't say that alkali is bad. Don't take that as a take-home message. So everybody is using alkali extra. It may be very good. Unless you do not know the other unwanted consequences, it might be.
As these compounds goes into the bloodstreams, they can contribute to the biomagnification, which is one of the main reason for different cancers and all these things.
Exactly,
And,
food chemical toxicology.
yeah. And one more point I want to add here, that in terms of the in case of alkali extraction method, it will be always deficient in essential amino acids like lysine.
Yes.
Lysine is attaching with some another.
I forgot to mention that point,
So-
exactly. Yeah,
so
yeah,
available
yeah.
lysine will be always deficient in these alkali
Absolutely,
extraction
thank you for
methods.
so much for bringing this point.
so
Yeah, yeah.
alkali-
So one point I forgot to mention, and he is clarifying it. I told that this lysine is reacting here, right? Lysine is an essential amino acid, and many plant-based foods contains low amount of lysines, and I'm reacting them it further now. Now the available lysine is further reducing, right? It's actually a problem. Good point. Thanks for bringing that up. Yeah.
That's all.
Good. Any other points did we miss? Yes, she has some points, conclusions. Yeah.
I have a question.
Yeah. Yeah.
Sir, when we are investigating some new protein,
Yeah.
and we would like to scale it up for the global audience.
Level. Yeah. Yeah.
So in that case, what should be our primary point of interest? Whether the yield or
Yeah.
the purity or the functionality?
Yes.
Or among these three, which plays a major role?
We're all fighting for this one. I don't have an answer for this question. So the conclusion here is that there is no protein that gives you, the method gives the highest yield, highest purity, highest functionality, highest nutritional benefit, highest health effect. No, it's a balance. It's a balance. It's a struggle that we are having today in this plant-based world. Okay. Well, how do we do this one? Usually food industries talk about yield. For them, yield is very important because the yield brings money, right? If you talk on an industrial perspective, yield is very important, purity is also important, but usually yield and purity go in opposite direction. If you want highest yield, you get lowest purity. Why? Because to get highest purity, you need to add another experiment, membrane filtration, dialysis, ultrafiltration, column chromatography, all these new experiments should be added. Every single step you introduce in protein processing, you compromise the yield. Something is lost. 5% is lost, 10% is lost. Every step, something is lost. You're getting higher and higher purity, protein loss is also increasing. So it's a battle. Yield is the primary governing factor. I agree with, because yield is important. Functionality is also, because some industries produce a big batch of protein with highest yield, highest purity, and they sell it to you. After spray drying, after alkali extraction, you come to know that, oh my God, I have a lot, but it's useless, right? And then you say, oh, it's the highest yield, highest water holding capacity, I can make a meat analog out of it, I'm very happy, I'm selling it to the consumer. Consumer eats it, and then the nutrition specialist comes into play, and he says that, oh my God, it's very functional, but the digestibility is only 70%. Okay, then you're unhappy. Then oh, the digestibility is 100%, everybody is happy, oh, it's very digestible, going into the stomach, going into the bloodstream, and then this guy comes, he's a health specialist, and he says, no, it has high amount of lal and lan also, and there is some study shows that lal and lan is bad for your health. I don't know it, it's not proven. Okay, there is a health concern. Where do we stop? It's again an iterative process. We always circling in the loop, right? At the end of the day, you need good yield, you need good digestibility and good health effect. It's just a loop. Research and development is required in this area. Nothing is the best, but I'm telling you that this unwanted thing could be maybe 5% is a problem, not 95% is. I don't say that every protein is damaged. 95% may be still safe to eat. Only 5% proteins are damaged. It's more about how much you eat every day. If you continuously eat damaged protein, maybe you have a health effect. If you eat once or twice in a day, just excrete it, because our body has a fantastic defense mechanism to excrete unwanted molecules. That's the beauty of human being, that's the beauty of animals. The problem, the health issue only occurs if you continuously consume unwanted things, usually. They're not poisons yet, right? The poison is also depending on how much you drink, right? If you eat small amounts of poison, nothing will happen, right? Smoking, alcohol, nothing will happen. Continuously eat, you get your liver damage. If you eat one bottle of poison, you might die, right? It depends, the minimum dosage, the LC50. I'm not a health scientist, but I know these things, but it depends. Did I answer your question properly? I don't have a right answer, it's a debate. Yeah.
So one more thing, the protein polyphenol adducts that are formed, is
Yeah.
it possible to be removed by membrane filtration?
Super good question. That's whole, we spent 3, 5, 4, 7, 6 years of work on this one. It's impossible to break this bond. We are not successful yet. There is no enzyme, at least we have identified, that can cleave this one. So if they are covalently bound, it's very difficult to remove. It's permanent. We could not identify any enzyme or a chemical treatment that can efficiently break down. We can use some reducing agent, yes, but as soon as you add a reducing agent and oxidizing agent, you also damage the proteins.
Yeah.
We don't want to damage protein, we just want to get rid of this reaction compounds. It's very difficult because food is such a sensitive molecule. We are not using it for the bioplastics. We are not using it for the, because soy protein can also use to prepare gum, glue. There you can do anything you want, nobody eats the glue, right? But food, we want to eat it. If you want to eat it, you have to be careful. I can do some chemical reaction to break this bond, but you can also break the proteins along the same way. It's a tricky situation.
Is there any method to identify
Yes,
the quantity?
we have a lot of LCMS methods.
Okay.
You can use untargeted and targeted methods. That's one of the expertise of our own labs. I do that research together with my colleagues and students.
Okay.
There are methods, yeah. I did not cover all these things at the interest of time, but we can talk about it later. Yeah.
I want to answer her question. These phenolics can be easily removed. Before going for the extraction, we can dephenolize the meal
Yes.
in which these phenolics are present. We can dephenolize the meal. After that, we go for the extraction.
I agree with you and I partially disagree with you also, because this is something we have done it so many times. We can actually dephenolize somewhere in this particular step, right? We can remove as much phenolics as possible, but it's impossible to remove every single phenolic compounds, because as soon as you bring the protein into solvent, a solution, as soon as you crush the seeds, phenolics actually located in one particular region of the seeds. They're not present everywhere inside the seed, but as soon as you crush them, they interact them. As soon as you put into solution, they are very happy. Now I can move everywhere, right? They can just attack proteins, whatnot. And there is a problem. It's very important to do, when do you dephenolize, right? It's impossible to dephenolize when the phenolics are covalently reacted with the protein. You can dephenolize free, non-bound phenolics, not the bound phenolics today. And this is something we are doing it with our rapeseed project. We are doing tons of experiment. In fact, it's actually the rapeseed protein powder, I should not tell it. Okay, I'm on a video. The rapeseed protein isolates actually look like this. We did a lot of dephenolization, we did a lot of purification, blah, 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 whatnot, we still have color. Tell me from where it's coming. Yeah. We have tried everything one could try to get the color out. It's not possible. Because, probably because of this we don't have a proof for this. This happened. Probably because of this covalently reacted compound, they are difficult to remove. The small amount of phenolics, they are present somehow. It's impossible to remove. Yeah, or less possible, less easy. It's very difficult. I don't say impossible. Impossible is a bad word to use in science. So difficult is the right word, maybe. Yeah.
I have a suggestion.
Yeah.
So if you have used a lower molar NaOH, based on my experience I'm sharing it with you, if the molarity of NaOH is less, then you get a more less colored protein.
Yes, exactly. Yeah.
And also the solid to solvent ratio, that also plays a major
Exactly,
role. Because if you are using 1:20 ratio,
Yeah.
you have to add more NaOH,
Yeah.
which gives more color to your protein.
Exactly.
So the less
That's where you play around. Again,
Yeah.
that you've come into the yield battle now. So then you compromise yield, because high alkali condition, more yield, more color. Low alkali condition, less color. Yes, yield is also compromised, but the industry wants yield, right? It's a battle. So no way. Is it clear? That was a fantastic discussion. At the interest of time, I need to give you a break. Let's take a 10 minutes break. Is it okay? I have to cover one more lecture, otherwise people will be unhappy. There are a lot of YouTube viewers. They're waiting for the next lecture. All right, so we take a 10 minutes break and we resume, and I promise you I'll give you a lunch break, okay? Yeah. Sorry. All right, so welcome to the day 2, lecture number 4. So we are going to talk about emerging technologies that can be used, those can be used to extract proteins from different biomasses. In the previous lectures, we discussed about conventional methods, salt extraction, dye fractionation, and so on. Now we talk a little bit more about the novel technologies or emerging technologies, okay? Some technologies I use novel because not well established. Sometimes they also use the word emerging technologies because again the reason is not so well established, especially in an industrial point of view. However, that is being done, I mean the work is done in the R&D level, research and development level. For example, a lot of laboratories use some of these some of these technologies to extract proteins, okay. I'll try to explain which technologies are actually scalable, which are not, what are the advantages and what are the disadvantages. Again, I start with the basic principles of their operation, then I'll show you some fundamental examples, some case studies and so on. Then again we discuss about advantages and disadvantages. Is it okay? If there is any question, raise your hand and ask. And I promise you, let's go for lunch at 1:30. I hope so. Good. You're hungry? Yes, so you're now. But is it okay to cover some next portion? Is it okay? Okay, keep your hunger. All right, let's begin with the ultrasound assisted extraction. I'm pretty sure every one of you have heard about this one, right? It's one of the most well investigated non-conventional extraction methods today. I can say that one. So basically ultrasound is actually a sound wave, right? You know about sound. When I speak, it's a sound. Every wave has a wave properties. You know that it has wave number, frequencies, all these things you have studied in physics, right? Ultrasound is a special kind of sound wave. The difference is that basically the frequency is like 2 to 10 megahertz and less than 100 kilohertz. Basically, this is the high frequency ultrasound is basically used in diagnostic purpose. If you go to clinics, they take ultrasound, they do some testing to see where the baby is moving and so on. And perhaps there they use this kind of frequencies. But in food science, for the extraction purposes, we use low frequency, high intensity ultrasound. Basically, we are talking about the intensity in the range of 10 to 1000 watt per centimeter square. The frequency is low, but the intensity is very high, and that can damage the tissues and extract the proteins out of the tissues because of their high intensity, okay. And remember my previous explanation, we have a cell, we have proteins inside the cell. We need to bring protein from inside to outside. What do we need to damage here? Cell wall we need to damage, okay. It could be plant cell, it could be microalgal cell. The cell wall has to be damaged. So conventionally we are using different technique. Non-conventionally here we are using ultrasound because ultrasound apparently can break the cell wall. Let's see how exactly that does, okay. So two types of ultrasound equipments are available today. One is the bath type, which is almost all chemical laboratories will have this bath ultrasounds. We call it as ultrasound cleaners basically. It's used to clean the system because it basically, because of the sound waves, it will reduce the particle size. For example, if you want to solubilize protein, if you want to solubilize polyphenol, if you want to solubilize amino acids, then you take it in a tube, put it in the ultrasonic bath and turn it on for 5-10 minutes, it will rapidly solubilize. Why? Because basically it reduces the particle size and improves the solvent solute interaction, right? Then they improve the solubility, and improve the solubility means actually increase the yield. Do you agree? Solubility is nothing but yield in our case. Increase and more solubility and we get more and more yield. Then there is something bigger ones called probe type systems. Basically these are more powerful and efficient than the bath type. In the bath type, what happens, the ultrasound comes from the wall or from the bottom. Okay? Sound waves first comes to the solution which is present outside the bath, basically it's water, right? The ultrasound first hits the water and then it comes to your matrix, right? Basically you already weaken the power here, right? But in case of the probe type, they take the, let us say, solution here, the matrix and the solvent and the solute, and they insert the probe directly inside the sample matrix, and then the probe, the transducer gives the sound waves, and that is directly interact with the solute and the solvent present in the sample. So it is more powerful and more efficient. If you really want to do the extraction studies, we recommend that you go for the probe type. I don't say you should not use bath type, you are welcome to use, but it is less efficient compared to probe type. And bath is extremely cheap compared to probe. This is a specialized equipment, they are more expensive compared to bath type. Depending on availability in your lab, you use whatever you want, but for the large scale protein production, we often use the probe type. Is it clear? All right. So now I'm going to explain you how exactly the extraction takes place. Okay. Remember, I have a beaker and I have a solvent, right? And my cells are here. These are my plant cells or tissues, matrix, microalgae, I don't care, right? Inside that I have protein, right? Inside that I have protein. Now I put an ultrasonic probe inside this one. This is the probe that generates the ultrasound waves. When it generates the ultrasound waves, the wave propagates in this way. We all know that the wave, how it propagates, right? When ultrasound wave propagates inside the solution, they create a negative pressure and the positive pressure, right? Positive pressure region is called as compression. What exactly here happens is that during the compression type, the solvent molecule that interact much readily, there is a more interaction between solvent molecule, and in the rare fraction cycle, they just try to go apart, okay? Together, apart, together, apart. That's what continuously happening. Together, apart, together, apart. At some times, the negative pressure increases, then they go apart, and basically at that time, they create a small air bubble, a vacuum, the vapor filled bubble. Okay, inside the solution, there will be formation of very micro bubble. You can't see it. It's not a big one, this size. A micro bubble will form. We are continuously applying the ultrasound. Basically, the bubble will slowly increase their size. Okay, and the vapor is filled inside the bubble. Okay, because you're continuously having this rare fraction cycle, so but the bubble will size increase. At a particular time point, a particular size when it reaches, it cannot increase again. So then you have a compression cycle, the bubble will implode. It's not explosion, it's an implosion. The bubble will collapse, right? When the bubble collapses, it releases energy in the form of heat. And they say that the temperature can reach all the way to 5000 Kelvin, otherwise 5000 degrees Celsius, extremely high temperature, but in a very localized region. And the pressure can be up to 50 megapascals, it's also high pressure. Now you create a high pressure and temperature right next to the probe and here, right? Now you have a cell here and you have a high temperature and high pressure, the small regions that is created. Now because of that temperature and pressure, the bubble, what we call microjets, very small microjets are created, and that will damage the cell. That will explode the cell, releasing the components from inside to outside. Does it make sense? This is the basic principle of ultrasound. This is called cavitation. The process is called cavitation. Okay? Basically, the waves propagates and they produce micro bubbles filled with vapors. At 30 particular time point, they cannot grow further, they implode. Implosion will create microjets containing high temperature and pressure, and that will damage the tissue or cells, releasing the intracellular compound into outside, and that is what we call extraction. So, ultrasound is nothing but an extraction assistance. It's not a real extraction, I would say. It assists the extraction by breaking down the cell walls or plasma membrane, whatever it is. Clear? Any question? It's the most simplest way I can explain this ultrasound. I can go deeper into subject, but that's not needed. Okay. Here is the microscopic image. This is a control sample, and this is a microalgae. So you can see that how it is actually damaging the cell. Once the cell damages, things comes out. That's called extraction. Coming to the equipment, so it's very simple. This is the bath type ultrasound here. Bath type operates around 40 to 45 kilohertz, and basically there is an ultrasound transducer. They produce sound waves, ultrasound waves here, and this is where water, and you put your beaker containing your protein matrix, you can do extraction, right? And the probe is very simple. You have a probe made up of usually stainless steel and produces ultrasound waves and damages the cell. Usually ultrasound is used in the batch system. Batch system means you have a solution, you treat the system, remove it, finished. That's often it is used, but there are some studies they show that you can also make a continuous system, means you continuously supply the matrix, what we call feed here, do the extraction and remove the feed. You can do that one, but I'm not very sure how feasible it is. It has its own problems. Okay, the batch type is most often used. But for food industries, tell me which one is more efficient? Continuous, because we need to save time and money. So this is something we really need, but this is we are at the moment. Okay. So this is a simple curve that shows how the extraction yield would look like. In ultrasounds, usually the yield increases with time, the time with ultrasound treatment time here, and then the yield can decrease. And sometimes the yield can continuously increase, then can come to a plateau. Now, can you tell me why the yield increases at some point, until some point? Increasing ultrasound treatment time increases the yield. Why? More explosion happens, continuously explosion action, any other components will increase, because you have more and more explosion, more and more cell damage, more and more things are released. And why is there is sometimes there is a decrease in the yield?
Once it is damaged, then inside particle is not visible.
Yes, but why we get the yield? For example, this is polyphenol. Okay, why the yield is decreasing?
Because it is the ultrasound is damaging further more duration is damaging the
Components.
we want to extract.
Exactly. So please note that people call ultrasound is a non-thermal technique, but if you continuously apply bath, you just see that the bath you put your finger, right? It becomes warm and hot, right? Usually some biomolecules are highly sensitive to temperature, and they can be damaged if you do a continuous ultrasound treatment. You increase the yield, yes, but they're also damaging them, because extraction and degradation goes in parallel. In this case, extraction rate is higher than the degradation rate. In this case, extraction rate is lower than the degradation rate. So degradation is overwhelming here. That's the reason why you see the loss. But proteins is usually not a problem, because proteins are stable. Okay? But if you're using ultrasounds for polyphenols, anthocyanins, bioactive compounds, you have to play around with the parameters. Okay? Usually this is the case for proteins. Continuously increase, then nothing to extract any longer, then it stops.
That's why its break is given, some 2-3 seconds pause.
Yes, pulses are given, exactly. Any question? No, yeah. All right, so this is one of the experiments we did back in the days with Chlorella vulgaris. Chlorella vulgaris is the microalgae that produces proteins. We try to extract proteins from Chlorella vulgaris. It's one of the most cited paper. We did a very simple work actually. What did we do is that we tried to compare whether or not ultrasound is beneficial to extract proteins. We did the conventional extraction with the different I think alkali and acid, and then we did the sodium hydroxide, then we did the ultrasound assisted extraction. Yield was very similar, can you see? Because the maximum you can extract is only 70% no matter what. But the only difference we saw actually the time. Basically you need to wait until 6 hours or 24 hours, but you can do it in 5-10 minutes. I don't say that ultrasound will increase the yield, but basically it becomes process more efficient, right? Basically time is money in industry, time is money, right? So within short time you can get more yield. It's not necessary always that ultrasound will increase the yield, but it is an aided technology. That means it helps, so you can reduce the time. It's a good take home message for you, right? If you want to do it quickly, because for example it's just simple, the same process, like you want to dissolve some amino acids, you can shake it for half an hour and it still dissolves after half an hour. But if you put an ultrasonic bath, 30 seconds it dissolves. That's where you save the time. That's the advantage of ultrasound. And there are a lot of parameters you can control for in the ultrasound. I don't go in detail at the interest of time, because you have a parameter to control the frequency, we have the parameter to control the intensity, and we have a parameter to control the time, and with a parameter to control the pulses. A lot of parameters you can control, but usually the intensity is the governing factor and the time, right? And if you apply more and more power, you can get more and more yield, and or less time within less time you can extract proteins or biomolecules. Is it clear? So a lot of parameters to cover: power, intensity, time of treatment, solid to solvent ratio, many things you can control. This is what people often do. There's thousands of literature on ultrasound on these parameters. A lot of response surface diagrams. Have you seen that one? They talk about how it is increasing. I did not write all these things because I thought it's very boring, because you can find it in the internet. So what your take home message is, you can control any parameters. However, usually the power and the time is the most governing one. The solvent and solvent ratio and all you can change to improve the extraction yield. Okay. Here I tried to summarize from this one. You can see that many plants sources have been used. Ultrasound treatment has been done on the many plant sources to improve the yield. You can see that people talk about 37% increase, 13% increase, 10% increase, so much percentage increase. It increases, okay? It's simply because it helps the damaging of the cell wall. It will help the reduction of the particle size. Please note that particle size is very important, because if you have a larger particle size and you have a solvent, and if you have a smaller particle size and this is a larger particle size and a smaller particle size, which one dissolves efficiently? Smaller, right? And ultrasound will help to reduce the particle size. That means there is a more interaction between particle and the solvent, because extraction is nothing but interaction between the particle and the solvent. So that interaction is enhanced because of ultrasound, so you get the better yield in addition to damage of the cell wall. Okay. All right, so can you mention one or two advantages and disadvantages? Ultrasound, what is the advantage? Yeah. Yeah. The time is money, it's less time consuming, the process efficiency will be higher. I agree with you. Any other advantage? Yes. One other claim is that ultrasound is a non-thermal process. Yes, ultrasound is a non-thermal process provided you maintain the power and temperature, power and time properly. Otherwise, usually the heating effect happens. I showed you that 5000 degrees Celsius. If you continuously heat, solution start boiling also, like it's super difficult. But ultrasound can also, you can also actually have a water chiller. Basically, you can control the temperature. So then you can prevent the degradation of the molecules. So the technology itself is non-thermal provided you control the treatment conditions. Okay.
Is disadvantage that installation cost is high.
The capital installment, the
Yes,
capital
initial
is
cost.
very high. Baths are not that high, it's cheap, but the probe systems are actually a little bit expensive depending on the size and the model. So, investment. Agree with you. Temple size is also limited. You often used in the bath system. If you really want to have a continuous system, you need to redesign it completely depending on the need. You don't know what is the flow rate and solid to solvent ratio. Everything has to be optimized. That's not a universal method here. So, it's not an easy one. I can tell you that ultrasound system is used in many cases, but it's not industrially well adapted yet. Okay, because some part of the world is still comes under the novel food category. So, especially in the EU, so it's still some industries are using, I know, but it's not that every single protein industry is using ultrasounds. That's not true. Okay. And another disadvantage is that the ultrasound probe what they use, apparently they say that after a long term usage, if you are using it in acid solution and a base solution, the stainless steel or the steel that start leaching the metal ions and so on, that might have some problem. And not only that, the probe what you use here in the solvent, and you have water molecule here, right, and the temperature I said 5000 and pressure some 50 megapascal here, and basically the water molecule is H2O, is basically HOH, right. It can have a homolytic cleavage because of ultrasound, and you get OH radical plus hydrogen atom. And OH radical is extremely notorious radical that can oxidize every single molecule, right. Super reactive, it does not discriminate protein, lipid, polyphenol, just attacks whoever comes right in front of it. That's one of the challenges, oxidation, lipid oxidation, protein oxidation, polyphenol oxidation can happen because of this one in extreme scenarios. And this is a strong reducing agent. This is strong oxidizing agent. So, there is some chemistry problem as well. Okay. Is it clear? Ultrasound is a good technology, increases the yield, but use it carefully. Can be used in the batch, but industrially it's not yet well established, still under the developmental stage. Then I will move on to the next technique called pulsed electric field technology. Have you heard about pulsed electric field technology? All right. It's not similar to ultrasound, but it's an equivalent technique, I would say. In ultrasound, we use sound waves, right. In pulsed electric field, we use electric field. That's the only difference, right. What do we do here is that we take a sample, it could be your microalgae, it could be plant extract, it could be potato, it could be carrot, anything can be placed in principle here in a solution. It will be water. There should be a solution is required, and that is placed between two electrodes. Okay, and we apply very high electric field. We are talking about up to 20 kilovolt per centimeter. It's actually extremely high field strength, right? And that pulse is given, it's not continuous applying the voltage, it's basically pulse. They give an electric shock basically. And we're talking about in nanosecond to millisecond, and the number of pulse can vary between 10 to 1000 or something depending on the type. So basically they're giving the electric shock continuously like this one. And that apparently damages the cell. Am I clear? So they are giving high electric pulses for a very short duration for a continuous time. Okay? It's not a continuous one, but a short pulses they give. At that time what happens, there is a principle that electroporation happens. Electroporation. Poration means formation of pore. Electro means electricity. Basically, the cells will have some pores because of this one. Now, protein is inside. When you have pores, what happens? They leach out. That's it. It's again an aided technology. It doesn't damage completely like ultrasound. It creates small pores on the cells, and apparently that helps to extract biomolecules, including proteins, so if the pore size is sufficiently big enough. All right. Now, how exactly that pore happens, I'll take it only 30 seconds for that to explain you. you put the sample, the biological cells in between the electrodes, right? These are the two electrodes, right? When you apply the positive and negative voltage here, basically there is a formation of electrical charge, the layers. Inside the cells there will be lot of ions, right? Some are positively charged, some are negatively charged. And outside you are applying the voltage, they basically start organizing as a dielectric barrier membrane now here, okay? And there is a particular electric voltage they maintain here. If you continuously apply this electric field at a particular electric field strength, the transmembrane potential, that is what the potential generated over here, is exceeding, and that will lead to the damage of the cell membrane. I am not talking about the cell wall here, it is a cell membrane, basically plasma membrane. So, there is a positive charge here and the negative charge here, and negative charge here and the positive charge. They have the transmembrane potential. And when you applied an external electric field strength over the transmembrane potential, they rupture. And the rupture is actually gives the pore, the hole. Sometimes this, that is called electroporation. The hole can be permanent, that means reversible, and it could also be irreversible depending on what the field strength you are applying. If it is reversible, basically the cells can rejuvenate. You can actually regrow that one. If it's irreversible, their cells will die. Basically, they leach all the cytoplasmic material outside, including the proteins. Okay? And the electroporation is the basic principle here. Ultrasound cavitation is the basic principle. Here the electroporation. This technology is also used in cell and molecular biology, you know. In molecular biology, they want to put a DNA from outside to inside. Have we studied molecular biology, biochemistry? They can use the same technique here, but we want the inside to outside here. That's the only difference. The protein, we want to get it out. I have some illustration to show all these things. I don't know, I have already explained this one, how the membrane opens up here and the things from inside to goes outside. Okay. This is some of the examples, microscopic image, just to show that how chlorella vulgaris cells will be damaged. I think in the paper they show that there is a hole formation here. I don't believe it exactly, it's really that hole because it looks so beautiful here. But basically the damage can be seen by this these cells here. Basically, when there is a pore formation takes place, they lose the cytoplasmic material, they lose the osmotic strength, osmotic balance, then they shrink. The shrinkage of the cell is direct indication of cell damage, okay? And that shows extraction of biomolecules. Is it clear? Shelf will shrink because of loss in the osmotic pressure. These are the commercial equipment, how it looks like. This is, I took it from the internet, but we have an equipment in our lab, but something similar to this one. Basically, it's a big machine because you have to do a lot of electrical stuff here because you're talking about 20 kilovolt per centimeter. It's a lot of electric field strength. And actually the cell is inside. Basically, it's a small piece of Teflon cell with the electrodes inside, and you put a sample. You can put carrot, potato, anything you put in solution, you can actually do. Historically, it's not used for the extraction, just to let you know. It's used for the drying purpose. Because you damage the cell and you make a hole, and the drying becomes much, much faster because the water molecule from the cells can evaporate much faster. So it's used for the potato a lot of drying technology, and also to soften the food material. Because when the tissue is damaged, it becomes more soft, then it has a different functional property. But people are also using it for the extraction. So you can see that the damage increases with increasing the electric field strength. Just to remember, just to show you that one of the important operating parameter is field strength. Increasing the field strength will increase the damage up to a particular degree, and then no longer you can damage the cell. You can skip this one. Yeah, just to show here about the efficiency of pulse electric field. I tell you that PEF or pulse electric field technology is used in the, it's not again not industrially well established, it's still in the research and development phase for the extraction purpose. It's industrially established for the drying purpose. It's already used in many, many industries, but not for the extraction purpose to the best of my knowledge. So when compared to high pressure homogenization, you know the technique they use, high pressure, the PANDA, the high pressure homogenization is a normal technique used to break down the cells. It's not that efficient. So it can be used, but PEF is not a really efficient technique, especially to extract proteins from cells that has very strong cell wall. Please note that cell wall cannot be damaged by PEF. Cell membranes can be damaged by PEF. To damage the cell wall, you have to apply extremely high electric voltage, and that we call high pressure, high voltage discharge. It's another technique, but it's not very energy efficient. Am I clear? To extract this molecule from inside to outside, it's not sufficient if you break the plasma membrane. You need to break the cell wall. But usually PEF cannot damage the cell wall efficiently. So it's not a really an efficient technique to extract protein, in my opinion, according to the literature as well. It does some improvement, provided you already damage the cell partially, then you can do it more damage with the PEF. It can be used as an aided technique. Okay. This is an experiment showing that how the field strength increases the yield. You apply more and more field, you get more and more damage to the cell, and more yield can be obtained. Okay. Okay, what are the advantages and disadvantages of this PEF technique according to you? I can conclude, I can summarize. PEF is nothing but it works based on the electroporation of the cell membrane. It makes the hole on the membrane because of the change in the transmembrane potential, and through that hole the proteins can come out. Okay. Then the extraction yield can increase. I don't say that it is a fantastic technique to get the highest yield in the world. I don't claim that one. It's not so efficient with the microalgae. We also tested it. It's very inefficient with seeds, for example, because seeds have such a strong seed coat. It's very difficult to make a hole on the seed coat with PEF. So it's not so efficient. We tried it with rapeseed. It did not really work out. So, but if you partially damage it with milling and other things, you can still increase the yield. Okay. What is the disadvantage and advantage apart from this one? Samples needs to be in solution. You can't have it in a dry state. That's very important. Yes. Anything else?
Cost.
Cost. The PEF equipment is really expensive. It's a capital investment, and then it can be done in batch and continuous. That's a possibility with PEF. We can do it both batch and continuous with PEF. The equipment are made for that one. The other disadvantage here is that the pore sizes actually matters. Basically, if you look into the, let's say, an animal cell here, it's easy to damage animal cell with PEF. The proteins are actually big molecules. Do you agree? And polyphenols are very small molecule. Imagine, I mean, animals do not have polyphenols. I'm just giving an example. The small molecules can easily come through. For the proteins to come out of these pores, that have to be sufficiently wide enough, but that is not always the case. So you need to optimize it a lot here, and it's also energy intensive process. Is it clear? PEF. You're welcome to use PEF to extract proteins, but if you don't get a lot of yield, don't blame me. Okay, that's a conclusion. Then the last techniques for today is enzyme assisted extraction. It's again a very well investigated technique. Okay, there is 10,000 articles on enzyme assisted extraction, not only for proteins, polyphenols, anthocyanin, pectin, carbohydrates, peptides, minerals, whatnot. Everywhere they're using enzymes. Again, coming back to my very first slide, this is the cell and the protein is inside. Who is the barrier here? Cell wall. Everybody is trying to break down this cell wall, right? Now, I told you cell wall is made up of what in plants?
Cellulose.
Cellulose, okay, and pectin and hemicellulose, okay. Basically, they are very complex network that is protecting the cell, right? Now, if I use an enzyme that can hydrolyze, that can degrade, that can dissolve the cell wall, basically the cell will open up like this. Do you agree? Then the protein will immediately come outside. That's the whole idea of enzyme assisted extraction. Now tell me which enzyme you will use to hydrolyze cellulose? Cellulases. That's something you studied in biochemistry. Aces are enzymes, right? Hemicellulose is a carbohydrate. Which enzyme will you use to hydrolyze it?
Cellulase.
Hemicellulase. Pectin is a carbohydrate. Pectinase. Okay. And protein is also some for example microalgal cell also contains protein on their cell wall. Which one you will use? Proteases. Basically what we use in reality, we use combination of these enzymes, not only cellulase, not only pectinase, not only protease, we use the combination of the enzymes to hydrolyze the cell wall to bring down the protein out. That's the only the phenomenon here. Is it clear? A lot of enzymes are available commercially, and this technique is used commercially also because it's easy to upscale this one. You can do it in a big reactor, you can do it in a small reactor, you can do it in open reactor, you can do it in closed reactor, it's easy. And enzymes are commercially available, you just buy, add and do the job, okay. I go a little bit in detail how exactly it is done. You take the protein as a flour, mix it within your solution and add enzyme and shake it. Things will happen, cell wall is damaged, you get the protein out. Again it's an aided technology, you can use an sodium hydroxide here provided enzymes do not die here. Many things you can use it in combination. Is it clear? It's just damaging the cell wall. I have a small, I don't go in detail for this one, this slide you can read it at home. It's not, but I just to show that for lignin we have different enzymes, for cellulase we have different enzymes, we have hemicellulose, we have different enzyme, we have pectin, we have different enzymes. For chitin, for example, insects have chitin, and also I think fungi also the cell wall is made up of chitin, then you have these enzymes. They are available in different combinations. You can buy it as a solution, you can buy it as an immobilized beads depending on your application, then you can buy them and you can use them, all right. Just to show one example is that it's not often a single enzyme doing the job. Just to take cellulose as an example, cellulase is a very complex polymer made up of glucose, but there's having a different network. Right, and initially you have endogluconase and cellobiol. This is, imagine this is a cellulose network. Okay, usually the endogluconase will actually cleave it here, and then you get an oligomers of cellulose like this one. Then there is a beta glucosidase, that is an enzyme that convert oligomer into monomers. Then in the hydrolysis happens. Same thing is true with hemicellulose and pectin. You can go through this slide later. Just to let you know that cellulase is not a single enzyme, it's a combination of different enzymes, they do different functions. They can cleave internally, they can cleave on the side part, they can cleave dimer into monomers. So you need to use the combination of enzyme to completely cleave into hydrolysis. But for extraction purpose, you don't have to do the complete cleavage. Do you agree? What is the problem if I completely cleave the cell wall? All things in compound, but if I, for example, if I convert every cellulose into glucose, what is the problem? Of course, everything, now the cell wall is completely dissolved, okay? What is the problem? Now I have a beaker, I have a cell, I have a protein, this is cellulose, okay, this is cellulose. I am converting every cellulose into glucose. Now I have protein and lot of glucose here, right? Separation again will be a problem, exactly. Cellulose you can precipitate by centrifugation because of fiber, right? It can be centrifuged and precipitated off in most cases. But if you convert into glucose, it's completely water soluble, then your life is gone. Then you have to again use another technique to remove the glucose ones. And not only that, the chemical reaction, glucose is highly reactive with protein, Maillard reaction. If you do it heating, glucose and protein react to undergo Maillard reaction, you get beautiful caramelized smell and other smell and everything. That's we don't want. So you need to control the processing parameter to get the thing what we really want. We just want it to open up, not completely dissolve. But if you are extracting glucose, probably you do this experiment, but that's not our aim. We want to extract proteins. This is the same mechanism, it's already in the slide, and this is a microscopic image showing the cell wall dissolution, that this is a cell wall with a staining and you don't see the cell wall after enzymatic treatment, okay. Okay, the enzyme kinetics I will not go in detail, but you all know that every enzyme has its own optimal conditions, right. They come with these bell-shaped curves. They have a pH optimal and they have a temperature optimal. It's recommended that you work in this particular region otherwise enzyme will be denatured. Sometimes they are reversible denatured, sometimes they are irreversibly denatured, the enzyme will be damaged. So, try to use the optimal condition, but it is always recommended that you do not work in this region. Can you tell me why? It is okay to work in this region in the enzyme, but not in this region. The denaturation, high temperature will irreversibly damage. If you really want to reuse your enzyme, then you can't use it, right? If you really want to here you will compromise the yield because enzyme is not super active, I agree, but enzymes are not dead here. If you want to reuse the enzyme for some other purposes, basically it's nice to use in near optimal condition, not on the right hand side, but on the left hand side. Make sense? So, do not try to target this particular, this is the danger zone actually. You get the highest activity, but you are also killing the enzyme here, okay. And this is a substrate effect. Basically, if you increase the substrate concentration extremely high, no effect you will see because enzyme to substrate ratio is very important. That you have studied in the biochemistry class. Please note that if you make an enzymatic process very efficient, there should be minimum enzyme and maximum substrate. Do you agree? If you want to load a lot of enzyme, the process efficiency is compromised because enzymes are also expensive. So, you need to find a right balance between enzyme to substrate ratio. Here is one example showing the alkali protease is an enzyme people have extracted. It has an optimal pH around 9 and optimal temperature around 60 degrees Celsius, just to show. You can do the enzyme kinetics yourself. Alright, now coming to the real experiments here. This is the protein extraction done on rapeseed matrix, okay, with and without enzyme, okay, and this gray region is without enzyme and this is with the enzyme. You can see that the yield is significantly increasing when enzymes are added. They are trying to use 4 or 5 different proteases here. They have different activities here. You can clearly say that the enzyme will actually improve the yield. Microalgae, it could be rapeseed, it could be soybean. Enzyme-assisted extraction is actually a good extraction technique to use, improve the yield compared to ultrasound and pulsed electric field. Make sense? You will really see, I have done it several times myself, you really see the improved extraction yield when you use enzymes, especially with microalgae. They are rough and tough, a cell wall, enzymes can actually cleave them in a very efficient way, okay. This is another example again with the rapeseed matrix. In this case they use, this is a no enzyme, this is with the enzyme called pectinex, it contains pectinase. You can see there is a rapid increase in the yield, okay. But usually people use the combined technique. That means you can combine ultrasound with enzymes. You do first ultrasound treatment, reduce the particle size. Do you agree? So, this is the big particle size and you first do the ultrasound treatment, then the particle size is reduced. Then you add enzymes. What enzymes need to attach to the substrate. Reducing the particle size means increasing the surface area. There is a more enzyme to substrate interaction and that will increase the process efficiency, otherwise extraction yield. Most often the recent article they actually use combination of ultrasound and enzymes to improve the yield. There is a lot of studies that show that is a added benefit, okay. So, you can use the combined techniques to use the improve the extraction yield. What are the advantages and disadvantages of enzyme-assisted extraction? Yes. Yes, enzymes are specific. That's the beauty of enzyme. That's sometimes it's advantage, sometimes it's also disadvantage. Yeah.
Optimization is very necessary for the efficiency.
Exactly. For every single substrate, you need to optimize. You need to find out the optimal conditions. Yes, good. And he mentioned it is a green technology because enzymes are environmental friendly because they are produced from natural resources, no chemicals, and yeah. But enzymes are also expensive. It's not easy. And other advantage and disadvantage is that if enzymes can be used in liquid phase and also in immobilized phase. If it is immobilized enzyme, it's easy to remove them. If it is a liquid phase enzyme, they are always present with your protein plus enzyme. Maybe the enzyme is a problem for you. You never know what it will, if you eat enzymes at the end of the day, it might damage something in your stomach. We don't want to do that one, right? Because enzymes are continuously active. For example, if you add a cellulase, you continuously store it in room temperature for 10 days, you get glucose at the end of the day, and some people will take that in to do the spray drying, then you have all the Maillard reactions, the whole protein becomes brown. So it's a problem. So you have to inactivate them. To inactivate enzymes, again you have to heat them. That's a problem. You cannot add chemicals to inactivate enzyme because we are talking about food. Again, there is a problem. The post processing is actually a problem with the enzymes. How do we inactivate it? How do we remove the inactivated enzyme? Please note that in food industries, it's not a problem when the enzyme is inactivated. They don't care. In the food industries, in the food industries, in food industries, it usually is not a problem if you inactivate enzyme, because enzymes are proteins, but the active enzymes could be a problem. Okay, that's the reason why you should not add enzymes in a lot of quantity. All right, that brings to the end of my lecture. So I'll try to conclude my today's lecture somehow. So we started with what? Lecture 1? No, we started with marketing. Okay, market is increasing, keep that in mind. Then we started with the conventional extraction. We started about dry fractionation, good one, but it's also having its own problem. Salt extraction, salting in, salting out. Then we are talking about alkali extraction, high alkaline condition extraction, isoelectric point, precipitation. But in every cases we have to remove the excessive salt, it's a problem. And alkali extraction brings chemical changes, it might be a problem. Then we talked about non-conventional extraction. We covered ultrasound, cavitation phenomenon, very efficient technique to damage the cell, very effective to reduce the extraction duration. Then we went to for PEF, electroporation, making the hole, very efficient in some cases, but not necessarily in all the cases. Seeds, it's very difficult to damage them. Strong cell wall, you can't damage them. Then we talked about enzyme, very efficient because most of the enzymes are very efficient in cleaving the cell wall and removing the compounds out, but post processing is required. How do we inactivate the enzyme? How do we remove non-inactivated enzyme? That's a problem. That's it for today. Okay?
Comparison on the yield of these novel technologies?
Yeah,
means application of this novel technology.
there is a lot of papers. I haven't put that purposefully because I could not find which one is the best one to say. Everything showing that, okay, there is an increment, this is better than the other one.
Means every extraction technique has its pros and cons.
Exactly, every single extraction has a pros and cons, depending on what you want, what is the facility you have, what is the end goal of the work, use that technique. That's the overall idea. Okay. Okay, then we are actually having the tutorial session. I'll get back to you on that one later. Okay, that's the last session. The lecture is over for today. The next one is tutorial. We take a break now, so thank you so much. Yes. Okay, so the fact is that we were